2, 1, 2, 2, 2, 1, 2. Okay, we are going to start our Tuesday session with the first talk by Valentina Giangreco-Paletti from University of Iceland, Probing Dynamics, oh, you see the title, of stringy flux tubes with large arc charge.
Thank you very much. Sorry, it's a long title, you're right. Well, first of all, let me thank the organizers for giving me the opportunity to talk here. And this is going to be a talk based on a work in progress with Davide Bonami, Valentina Florini, Luca Griguolo, and Domenico Seminara. And in particular, Davide and Luca are here among the audience. I have some problem in switching of the slide. Let me go like that. I think so, because the pointer works. But maybe I can do it by hand.
No, but it can you try again?
Like that?
Ah, that's better. Can you try again?
Now, thank you. Okay, good. Our motivations. Well, I guess I don't have to explain this audience the importance of Wilson loops. Of course, these are very important, observable, gauge invariant, non-local. And they have showing very interesting properties, for example, then playing an important role in confinement, deconfinement. And I guess also I don't have to explain, but I want to say, because at least it's my personal motivation, how important to study certain objects, indeed as a Wilson loop within n equal 4 super Young mills in 4 dimensions, but also other, let's say, key in QFT. And my personal motivation is because this gives you an interplay which is quite ideal and amazing to study, to show how different notions and techniques coming both from quantum field theory and from string theory play an important role and then can combine together. So that's my, as I say, my personal interest in Wilson loop and the formation, and in particular in the ERC-CFT. And as I say, my personal interest is that it could help also to understand a bit better what's going on the string theory side. And okay, in this talk I will focus on a particular family of observables and in n equal 4 super Young mills. And this is what's called cusp Wilson loop with local insertions. So they are deformed by a geometrical angle that I'm going to call cusp. They are deformed by orientation angle, sometimes I call it also internal angle, theta, and by the insertion of local operators. And this is general, so I'm going to be precise in a moment. But the goal is that I want to study this Wilson loop from the point of view of the string theory. And in particular, the goal is to go beyond the classical level. And the question that I'm going to try, at least partially, this is a work in progress, is going to try to understand which are the features that can string theory, or at least the dual string theory, can capture about these observables. Okay, and please, you know, if I'm saying something not clear, just interrupt me and ask questions. So I'm going to try to review a bit, very quickly, what these objects are in n equal 4 super Young mills, and then I'm going to review the classical solution dual to these observables, and I'm going to try to go through an example a bit more detail, a specific example which is called the anti-parallel limits, and see what's coming out of this analysis. And then, okay, let's see how far I go, but I'll try to also go to the one loop level and discuss outlook and extension. Okay, part 1, field theory. So let me start to be precise. Of course, the central object here, it's the Wilson loop. Well, let's say the Wilson-Maldacena loop in in n equal 4 super Young mills from the field theory side. And just to be clear, I'm going to work only in the planar limit, so n is very large here for us. And at some point, I will switch also to the strong coupling. This is, of course, is the general definition, but I'm going to be interested in a very specific case. And what do I mean? What we call the generalized cusp. So I'm going to place first the theory on R times R3. And I'm going to consider a loop which is made by 2 lines separated by an angle, pi minus phi, in our convention, on the big circle of S3. And these are extending along the time direction. It's very important for us. They are very long extending. So it's going from minus infinity to plus infinity, essentially. And I'm going to ask that the orientation of the 2 lines, there is a relative angle theta. This is what we call it the internal angle. So this is a bit the pictorial picture of the generalized cusp. There's been a huge amount of work, and I guess this audience is quite, you know better than me what has been done here. It's important to, at least for me, for this talk, what's important to remember that we can see the cusp in 2 different ways. So if I think of this picture, let's say once you weak rotate, you can interpret this potential, the Wilson loop, essentially as an effective potential between 2 heavy probe charges in n equal 4 super Young mills. So this is the one way to look at this Wilson loop, as an effective potential between a quark-anti-quark pair. And of course, this is generalized what has been done in flat space. Okay, and so where basically this distance is giving you in flat space the distance between the quark-anti-quark. And there are very important results, and they play a huge role, of course, in the history of the SCFT. But of course, we can use exponential map with rotate, and we can see this also as a cusp Wilson line, that hence the name. And so now the angle between the 2 lines is given by pi minus phi, as we say before. And okay, we have to think about that there is an orientation between the 2 lines. This Wilson loop, having a cusp, has logarithmic divergences, and in particular, here I am, the this called indeed cusp anomalous dimension is what control these logarithmic divergences. And so since these are related to conformal transformation, we basically read, I'm going to switch, and sometimes I'm going to talk an effective potential between quark and quark, and sometimes I'm going to call it a cusp anomalous dimension. So here I'm underlined that there is lambda, of course, the two coupling that depend on phi, as I say, geometrical angle, and theta, the internal angle. Okay, I'm not done yet, in the sense that I want to do something more on this. What do I mean? I'm going to insert L local operators along the loop. Not any local operators, but I'm going to insert the scalars that are sitting here, Z and Z bar. And okay, in this picture, we are inserting to plus and minus infinity. And what is important for us, and these are the scalars which are not coupled in the Wilson loop. So these are sometimes called orthogonal. Okay, so in such a way there is no interaction. Okay, this plays a very important role, in particular, for example, for deriving the TBA of the cusp anomalous dimension itself. So this is it's an observable that plays an important role. I've added here an L because now this is going to be another parameter to add to the description. And okay, if I go back to the description of the cusp Wilson loop, this for us is going to sit indeed at the cusp. So we are placing zeta L operator at the cusp. Now this is the object in the field theory side, but now I'm going to switch off to the dual side. So I want to study this object from the string theory perspective. And so we are studying this at strong coupling, so lambda is going to be large for us. But to have a semi-classical description on the string, we need to have also L to be large. So this is important because it plays an important role for us. Okay, so let me go to the string theory side. Well, I have to, maybe everybody knows, but a fundamental, so a Wilson loop in the fundamental representation is holographically dual to an open string. And important to remember that the worksheet ends at the boundary of ADS5, ends at the loop itself. Now, the way that we can think about this insertion of operators, essentially in the semi-classical description, is like you are fluctuating your worksheet. And I'm going to be a bit more precise in a moment. And as I say, what's important for us to remember, there is a hierarchy of limits here. So there is a large N, large lambda, and there is also a large L, this R charge. Okay, so the plan now, since we are thinking about a semi-classical description, what we need to do is, of course, first look at the classical solution. So you have just a classical open string in a DS5 cross S5. And then we want to go beyond one loop. So this means take into account correction for strong lambda. And so this means, so basically look at the series 1 over square root of lambda. And so we are looking at fluctuation around this classical string solution. Okay, that's the plan. Okay, so for the time being, I'm going to focus on the classical string solution, so just to, which is dual to our observable. And this was obtained quite some time ago, actually. First in Drucker-Kawamoto in 2006, and in particular for the case when you have the insertion on the straight line, okay? And then was generalized later with the two angle theta and phi. Okay, I'm going to spend some time on that because it's important that it comes out. You understand what the object that we have. So, okay, the string worksheet coordinate tau and sigma is between an interval minus s half, and we are going to determine what it is s in a moment. And so what do we have? So let's look first on the ADS3 part, which is inside ADS5. So, okay, we wanted the worksheet end at the boundary on the loop. So this t of tau, it's representing indeed the running along the two lines, the time direction. Rho is the radial coordinate. So the string, of course, is ending rho going to infinity. It's the boundary of ADS. And then, of course, the string, it's moving inside the bulk. And then this is an angle, so there is a rotation. This is written here in this embedding coordinate. And this is the angle that when you reach the boundary is going to give you the geometrical angle of the quark-antiquark. So the separation of the quark-antiquark has to be pi minus phi. Okay, and then of course there is nothing else in the other two orthogonal direction. Now, if I look on the compact part on S5, what do we have? Well, okay, there is theta, var theta, I should say, which is, again, it's connected to the jump on the S5, that the cusp, remember, there is an orientation of different orientation between the line. So this is, of course, is related to that. But then we want to insert the operator. So there has to be an angular momentum. And so this is the omega tau that is going to describe the angular momentum related to the R charge. Now, notice that this is what I was trying to say before. This is in two planes which are orthogonal, okay? And so this is, of course, is the plane which corresponds to the coupling of the scalars. And then, of course, y5 and y6 do not play a role. So important for us, this is related to theta, the internal angle, and this is related to the R charge. Okay, this is a pictorial picture. Well, I don't know if hopefully it doesn't confuse more than what it's supposed to be, but it's just trying to put in picture what I'm trying to say. And of course, this is the boundary condition that I was trying to explain here. So when you reach the boundary, you need to reach the Wilson loop, which is described by the two angles, the geometrical and the internal angle, okay? Okay, let's see what we, okay, this I said in Word. So I'm not gonna go, well, okay, maybe one thing that I forgot to say, it's in this picture, the two insertions are basically at plus and minus infinity. I'm working in global ADS coordinates, okay? So what from the discussion before, the induced metric of the worksheet, it's ADS 3 times S3. It's written here. And let's start now to understand the parameters and the charges that we have here. Okay, so if we look at the equation of motion, d and omega, so these are depending on the tau coordinates, going from minus to plus infinity. So these are essentially given by they are proportional to tau, the worksheet time, and kappa and gamma. These are two parameters for the time being, okay? And we are gonna say more about that in a second. There are, of course, the correlative conserved charges, E and L. So in particular, E is the conserved charge with respect to time, and then L with respect to the angle omega. There are also two conserved momenta, since we have cyclic coordinates, and in particular, there is L theta for the rotation on theta, and, sorry, this should be actually var theta, sorry, and this L phi related to the angular momentum, it's the angular momentum related to the angle phi. Okay, so that's the setup. You can compute, for example, in conformal gauge, you can use Polyakov action to compute your string action. And of course, still I have to tell you the equation of motion for rho and for psi, the angle, in S5. And actually, it's easier to work with the Virasoro constraints. And these are the two Virasoro constraints that we have. Okay, they're important to notice that there is a kappa and L phi, and here there is a gamma and L theta. And of course, I mean, if you see it, there's basically an analytic continuation, one of the other. Okay, so there are two conserved charges, two boundary data, the two angles, and there are four parameters, okay, gamma, L theta, and kappa L phi. But this is not the end of the story, because there is an extra relation. I told you about the extension of the string, which is S, and of course, you can compute this parameter either integrating rho or integrating psi. And so these two quantities, they have to be equal. This is nothing that say that basically you have to impose the Virasoro constraints. That's another way that you can think about this relation, okay? But it's gonna play an important role. Okay, so these quantities were already computed in 2012, but I'm gonna go over, because there is a technical caveat that's gonna play a role for us. So please bear with me with the technicalities, and if it's not clear, just ask me. Okay, so we can switch. It's easier to work on with the Virasoro constraints, switching coordinates. So I'm going to switch to this R. GS stands for Gromov and Sever, since this is the notation used, for example, there in 2012. And I'm going to look at the Virasoro constraints. And, okay, this is a quantity which is positive, so left and right side should be positive. So first of all, you analyze immediately that this gives you a fact that there is a minimal distance. What does it mean for the string? The string is moving when sigma is going to 0 to the center of ADS and reaches a minimal distance, okay? It's not necessarily, it's not reaching the center of ADS. Okay, but in order to integrate this equation, you have to tell me where is the order of the poles. And so if this A minus is less than -1, then you are scanning, let's say, the parameters L5, which are between -1 and 1. This is just, math. It's nothing more than that. And then for the second region, so if A minus is greater than -1, once you integrate, you are integrating in a region which L5 is between -1, 1. So what does it mean, this one? This is simply you are living in this space of parameters, and the two regions are simply related by modular transformation, because once you integrate here, you're going to get an elliptic functions, elliptic A, elliptic kappa, and so on and so forth. And these two regions, so when you're switching from one to the other, are just simply related by modular transformation. So it's important to understand there is only one energy if you want. It's just that this is a way to, to avoid to deal with modular transformation. You can think also in this way. Okay. All this, so this A and this B has gone a label to remember myself in particular in which part of the parameters I'm looking at. And these are all functional L5 and kappa. And this is what I was saying before. Okay. You can repeat the same story for the compact part. But slightly different, because now you have a sign of psi, which has to be always between 0 and 1. So in some sense, okay, you have still a minimal distance. This is telling you how much the string, once you move it towards the center of ADS, how much the string is reaching. So there is a, let's say, a minimal distance, also minimal radius on the sphere in which the string is sitting, and it's keep on rotating. And in particular, as I say, since this is a sign is always, it has to be between 0 and 1 if we want to have physical solution, this is imposed basically only one region. So you can scan between the parameters only between -1 and 1. These are the physical one. Okay. And so also L, theta, and S are all function of these parameters, gamma and L theta. In particular, L theta has to be between -1 and 1. Okay. Here, just to make you understand, because these letters maybe don't mean anything to you, but essentially when you are reaching 1 and -1, basically you are switching off. No, basically you are switching off the air charge, just to understand. And if L theta is equal to 0, this means essentially you are switching off the jump on the sphere. Okay, so basically you're switching off the angle, the internal angle theta. Okay, questions about that? Is it kind of clear what I'm saying? So here I'm just analyzing classical solution and dividing the different parameters, just for understanding. Okay, what are the consequences of this, if there are any consequence? Yes, this is what I was trying to stress before. There is everything is continuous. There is only one energy, one cusp. Everything is continuous. Okay, so this is exactly what I said before, just rewritten here. There is another small caveat that I have to tell you, is where is among the, so as I said before, we have this S, which is the interval in which the string coordinate it's spanning. And if I'm looking at the value that we can obtain from the parameters available on the compact space, this is spanning between 0 and infinity. But if I'm looking at the value that that I can compute, starting from ADS quantity, there is an interesting distinction. If I am in the region A, so this L phi greater than 1, oh wow, 10 minutes, okay? Okay, see, thank you. Then it's only between 0 and pi. And if I am instead in the second interval, so when L phi is between -1 and 1, this can span between 0 and infinity. So one case is bounding, the other case is not bounding, and this plays an important role. Okay, this is the string action, and I'm going to use G, which is basically square root of lambda, quite a lot. Okay, so somebody could say, and then what? Here comes the point. So I'm going to focus on the energy, and in particular, I'm going to look at the potential energy. So how do I think to this energy, the quantity that we are discussing before? Well, I'm looking the potential energy as the energy between these probe charges at strong coupling, and I want to study this in presence of this local insertion. And so I'm thinking about that as energy let's say, as an excitation of the energy among the quark-antiquark. That's one way of thinking about it. And I'm going to take in doing this, what I have to look at, I want to look at these antiparallel limits. So this means that we are taking. Okay. Well, then you have to sit down and compute. And what do I get? So if I am in region A, what do I get? Not surprising, something which goes like pi minus phi, 1 over, sorry, pi minus phi. This is indeed the quark-antiquark potential. This is the Coulomb-like singularity that we all expect and that we have been computing in the past. And then correction, which goes like pi minus phi and so on and so forth. So this coefficient, these are functions of the parameter k naught, and this is a combination of L phi and kappa. It's just as convenient for this relation, doesn't matter for us. But this has to be computing, and of course you have to impose the Virasoro constraints. So this means you have to satisfy this equality. What does it mean here? Just to be clear, I'm fixing L and theta, so this means I have an S compact, if you want, SS, and then I need to match, of course, the Virasoro constraint. So I'm going to find my K naught in such a way that this equation is satisfied. Otherwise, I have no string solution. Okay, I can repeat the same exercise for the B region. And what do I get? Well, I'm taking the limit, phi goes to pi. I'm going to take an L and theta fix, and I get something completely different. What do I mean? So it's a constant plus correction, which are actually quadratic in pi minus phi. And again, this is the parameter kappa naught, which has to come from satisfying the Virasoro constraint in this region. Now, there is a difference. This value is spanning between 0 and pi. Here, I'm spanning between pi and infinity. Okay? So this is something that needs to be understood correctly. So here, I'm zooming to very close. So you see this is the behavior, and this is the typical Coulomb-like potential. Okay, so how can I understand better what's going on? So instead of fixing L and theta, what I'm going to try to do now is fixing theta and see how this energy changing when I vary L, okay? So it's just slightly a different approach. Now, where is the problem here? Let's say the problem. When I moving from one region to the other one, so basically the value of pi, you see, this is the value that, it's basically delimiting the two regions A, what I call the two regions A and B. So what I am going to do now, I'm going to focus essentially in the value of this S compact, which is fixed and close to pi. And for the way that we are constructing the equation, the solutions, essentially I can keep this fixed by either varying L or theta. What do I mean by that? There is an entire value. So you see this region, if I'm looking here, so here are all the points in which I have all this S fixed. So this is the interval for the strings fixed to pi. And these are, I can choose different. For example, I can fix L and vary theta in such to keep this S fixed to pi, or vice versa. So this S plays a kind of a role of an effective angle. I don't know if this is clear or I'm confusing you. It's kind of clear what I'm saying. The silence usually is not a good sign. It's like when you ask to the students, do you understand? Silent. What I'm trying to say is that essentially you have three quantities, S, L, and theta, but you have two parameters, okay? And so you can play with that essentially in such a way that, as I say, you fix the interval to be pi, but you can, how you reach this pi, you can choose either varying theta and fixing L or vice versa. And so this is the, this region. So I call it critical line because this is the pi, it's the value that separates the two regions A and B above pi. Okay, and so if I'm use this information and I'm look how the energy is varying with L minus L critical, so here I'm fixing theta now, varying L, and I'm looking the two regions how this is varying. And you see immediately, so we are still in the antiparallel lines, we are only working the antiparallel lines. There is this 3/2 coming here, and there is 1/2 coming here. Okay, 5 minutes. So what is going on here? So here the energy is negative as we expect, and this approaching the critical value with an exponent which is 3/2. When you reach the L critical, the energy vanishes and it's start to increase. So this is actually positive when you move to the next region. So, and in particular, it's increasing with a power which is 1/2. So the energy quantity is continuous, but of course it's not differentiable. You can compute this quantity here, it's just an expansion, Taylor expansion. So we have it also, of course, either numerically or analytically. So this is a plot in 3 dimensions. I can see now it's very pale. This is the plane, which is L equal to L critical here, and this is the energy versus L, and these are the value of phi. So towards here you have pi, and this is going to 0. Okay, so this is what it's going on. So as I say, it's continuous but not differentiable. Okay, so the question is what is going on? I think the main message was already understood quite some time ago. So the classical solution here, what it's doing, encodes this transition from the Cass-Wilson loop, basically when you have L equals 0, you don't see the insertion, to a kind of BMN-like vacuum, where you see only the insertion. This is what's kind of, I think it's the correct message here. What does it mean? Well, it's basically you are, I think also maybe it's clear in the spin chain picture, you have this zeta L. When L is very large, you're basically probing this trace to the zeta L if you want. It's some kind of BMN-like vacuum. But if L is not that large, then you start to see the endpoints of the chains, which are basically this Cass-Wilson loop, which are, so it depends on the theta and the phi. So I think this is the message that we are seeing. And so they were looking, for example, for the special case of phi equals 0, this so-called Lusher correction or wrapping correction along in the paper by Correa, Maldacena, and Sever in 2012. So when L starts to be large, so your L, as I say, you are proving basically the size of the chain, the energy minus the L, it's going to 0, so it's kind of going to a BPS state, but with the exponential correction. And we see this in our computation with for generic phi and theta. Why this is important for us is essentially we need this region to reach this value, because here we are always bounded to have a maximal L in some sense. So if we want to approach very large L, we need to be in what we call this region B. So this is the one that allows you to connect essentially with the BMN vacuum and with the Lusher correction from the spin chain point of view. Okay, so this is what I'm saying in Word. Now, I can look also, so we talk about BMN, and so we can think about also, can we see this BMN spectrum? So this is an initial analysis was done in 2006 in the paper, as I say, by Druck and Kawamoto, and we see this coming out from one-loop computations. So if we have the full Lagrangian for the one-loop computation, and we see the emergence of this BM spectrum, so if we take this large M limit. So, and again, this has to be connected again to the large L, so it has to be coming from region B. So, okay. Okay, there is another paper which is playing an important role. Okay, then I'm just suggesting one sentence of this paper. So this is a paper from 2006, not very cited. And they were studying the quark-antiquark potential in flat space-time in the presence of this L massless scalars field. And there, the way that they think about, okay, it's in the language of QCD, this quark-conium, they interpret this going to 0 of the energy, like basically the binding energy, it's vanishing. So after that, you have an unbound state. You're describing unbound state. But for some reason, they do not continue. So they kind of stop at 0, and they do not move for, they don't have a region B in some sense. That's the way of thinking in our language. Okay, what about loop correction? Well, the question that, as I say, I was trying to answer before, do we see the BMN spectrum? Well, the quick answer, since I have less than 1 minute, yes, at least from the analysis of the frequencies that we have been doing now. And the other question that, of course, is crucial for us, does this transition, I should call it quotation mark transition, survive at one loop? As far as we can see from the analysis of the frequency that we have, the answer is yes, even in some sense it's a kind of a classical mechanism. and bosonic for the fluctuation. So these are fluctuation around the classical solutions. And we are studying the frequencies for these modes. And so far, what we have been doing is just looking at the so-called easy modes, in some sense, the one which are decouples, because it's a bit, well, the masses are not that trivial to, in order to compute the frequencies. Okay. Okay, that's what I was saying more. That's the summary. And I guess I have 0 minutes. And that's the to-do list. So I'm going to just focus on the to-do list. Of course, we want to compute the one-loop analysis, continue with the coupled, let's say, modes. We want to look also for different limits. So here we focus on the anti-parallel limits, but we want to look, for example, near BPS limit. If there is something we can say, this is all strong coupling, at the correction strong coupling. So we would like to see if there is something that can be said from, there are data coming from the quantum spectral curve, from the TBA. So can we say something about that? And then there are, of course, many other things to be done. So this is just a list of the one that I think I consider it interesting to explore. Okay, thanks for your attention.
Okay, so questions?
Ooh. Yeah. Hi. So could you remind that at weak coupling, I think there is pole at NEL if L is fixed at weak.
Say it again, sorry.
At weak coupling, there is a quark anti-quark pole at
yes,
NEL.
Yes, that's true. That's true. That's true. That is also true at weak coupling. Yes. Is that?
Is so near L critical, if you consider L to be continuous, what kind of, how did you analyze the transition?
Yes, that's classical level, you mean?
Yeah.
Yeah, this is what we are looking here, essentially. Well, both for the action, this is always in the anti-parallel limits. So this means close to L critical, phi goes to pi, and then I take my theta fixed. That's and so this is, it's continuous, but there is like a kink in the action, and the same is true for the energy. I don't know if it's visible in this mathematical plot, but so the energy goes like that.
One last more question.
Okay, I feel a bit uncomfortable to call it transition because there is one solution. If I think of phase transition, I usually think about an interplay of different solutions, and then your free energy is as a king. I don't know, maybe, yeah. So there is one solution of the string, as far as I understand. So that's why I'm using quotation marks. And it's in some sense, yeah, that's the answer.
More questions? Well, if there are no questions, we thank Valentina again. So the next talk is by Stefan from Imperial College. Title will be on the screen soon.
Okay, thank you very much for the invitation. In this talk, I'm going to discuss non-planar corrections to anomalous dimensions of primary operators in ABJM theory appearing from semi-classical M2 branes. And this talk is based on 2 works published with Simona Giombi and Arkady Tsetlin, and with Matteo Beccaria and Arkady Tsetlin. So in gauge theories such as n equals 4 Sapien Mills or ABJM theory, anomalous dimension of operators in 1 over n expansion may be written as a function of lambda at each order in 1 over n. The leading term, which is just the planar part, is controlled by integrability and in principle can be determined as exact function of lambda. Less is known about non-planar corrections. For instance, in the case of n equals 4 Sapien Mills, they are computed at weak coupling. For instance, for cusp anomalous dimension, the non-planar correction appears at the fourth loop order, and similarly for Kanishka operator, in n equals 4 Sapien Mills appears.
Attention, please.
Sorry.
Attention, please. The fire alarm is about to be tested. Please take no action.
Okay.
Attention, please. Attention, please. The fire alarm is about to be tested. Please take no action.
Okay, so coming back to non-planar. Okay.
Attention, please. Attention, please. The fire alarm test is now complete.
Okay.
Please respond to all future fire alarms.
Okay. So I guess that means that we can continue with non-planar corrections for at weak coupling. So they're computed in n equals 4 Sapien Mills for cusp anomalous dimension and Kanishka operator. Both appear at the fourth loop order, and by making an analogy, and less is known about ABJM theory, but by making an analogy between these two theories, one can also expect that for these quantities, the non-planar corrections will appear at the fourth loop order. Much less is known about strong coupling, and there are no predictions for anomalous dimensions from the gauge side. However, one can consider another quantities which are protected by supersymmetry, such as, for instance, free energy or BPS-Wilson loops, for which the result is known from localization, which is exact in both 't Hooft coupling and also N. It was recently shown that M2 branes, well, some classical approach to M2 branes in both ADS4-S7 and also ADS7-S4 reproduce the leading terms for these protected quantities. Well, in particular, 1/2 BPS-Wilson loop, instanton contributions to the free energy in both 3-dimensional ABJM theory and 6-dimensional 2,0 theories. This provides a motivation to apply the setup to non-protected quantities such as anomalous dimensions by using this semi-classical M2 brane approach. So in this talk, I'm going to review the semi-classical M2 branes and consider like one of the examples where the result is known on the gauge side, which is 1/2 BPS-Wilson loop, and then I'm going to explain how to apply this logic to anomalous dimensions. So let me start by reviewing the action for a supermembrane. So the supermembrane action of the Green-Schwarz type was suggested in the paper of Berkshire, Seshkin, and Townsend, and its bosonic part describes a 3-dimensional surface interacting with Ramon-Ramon field. One can add fermions by considering L11D superspace, which contains 32 components Majorana spinors. And the action also contains the so-called like Vezumino-like term, which can be expressed as an integral of a closed 4-form over a 4-manifold whose boundary is M2 brane. So for instance, in flat space, the bosonic part of the super coframe and the 4-form appearing can be written in this form. The Vezumino term is important to ensure that the action has the so-called kappa symmetry, which is a local symmetry. And it is essential to reduce the independent degrees of freedom for fermions by 1/2 so that on shell the bosonic and fermionic degrees of freedom match. So it can be written in this form, where gamma can be thought of as a fermionic project expressed in terms of 11D gamma matrices and determined by the M2 brane. Another important property of M2 brane action is the so-called double-dimensional reduction. Namely, one can consider an 11D background compactified on a circle and also assume that the rest of the fields are independent of the coordinate in the circle direction. Then one can consider M2 brane in this background and assume that it wraps the circle and also fix part of the Wald volume diffeomorphisms by just identifying one of the directions of M2 brane with this circle direction and requiring that the rest of the directions are independent of this Xi2. Then one can perform a what is called double-dimensional reduction. It is reduction in both target space from 11D target space to type 2A target space, and also reduction on the Wald volume theory of M2 brane, which just gives the Green-Schwarz action in this type 2A background. Although there is a relation between Green-Schwarz action and M2 brane through this double-dimensional reduction, the quantization of small M2 branes is much more subtle. Well, for instance, the theory is nonlinear. However, one can argue that there is an analog of Lycon gauge for M2 brane in which there is a relation to quantum mechanics of ND0 branes, which suggests that the theory of small supermembranes has a gapless spectrum. Another problem is apparent non-renormalizability of M2 brane action, and in fact, it was discussed in a recent paper by Bikaria, Roiban, and Zeitlin, in which they considered 2-to-2 scattering S matrix for M2 brane, which is in flat space, and they considered this matrix for fluctuations around this M2 brane. And what they found is that it contains a genuine UV divergence at two-loop order. This, however, doesn't mean that other observables, as for instance partition function for M2 brane in AES space, will be UV divergent. In this talk, I will focus on M2 branes in ADS 487 background, and I will consider a semi-classical expansion around classical solution with non-degenerate metric. And I will also consider one loop order which is UV finite, so these problems will not appear there. So to obtain at one loop order semi-classical expansion, it's just enough to consider a quadratic action for both boson and fermions. The bosonic quadratic action can be written in this way, where there are F4 terms due to interaction with Ramon-Ramon 3 form, and the rest can be written in this way, where everything is expressed in terms of geometric data, which includes Riemann tensor of the background, and also geometric data of the classical surface, which is extrinsic curvature K, and also derivatives become derivatives in the associated normal bundle. The fermionic part can be written like that, where the derivative is just the pullback of 11D killing spinor derivative, and here gamma appears just as a result of kappa symmetry at the quadratic order. A convenient choice to fix this kappa symmetry is to set gamma theta to minus theta. So then the semi-classical expression, for instance, for partition function takes the following form. There is a classical exponent, then there is one loop piece coming from operators in quadratic action, and then there are higher loops terms. So this semi-classical approach has been tested for several quantities. Maybe I should also mention that here usually you have M2 brane in some curved background, so you have a scale, for instance, as radius of ADS or S7, and you can introduce effective tension, which includes the scale. So the expansion then is in terms of the effective tension. So this semi-classical approach has been tested for several quantities for which the result is known from the gauge side, which includes expectation value for 1/2 EPS circle Wilson loop in ABJM theory, associated with it Brem-Stralsund function in ABJM theory, and also instanton contribution to the free energy on 3 in ABJM theory. And also, in the case of 6D 2,0 theory, this includes surface defect conformal anomaly and giant graviton contribution to superconformal index. So in the rest of the talk, I'll primarily focus on ABJM theory. So let me just review some basic facts about this theory. So this is n equals 6 superconformal theory with the gauge group un times un. It has Chern-Simons level k and minus k. So in the superfield components, it can be written in the following way, where there are 4 bosons in B fundamental representation of the gauge group, and 4 fermions in the B fundamental representation of the gauge group. And bosons acquire sextic potential, while there is also mixed potential between bosons and fermions, which is quartic. The Chern-Simons level appear as an overall factor, k, so it can be considered as Young-Mills coupling in this theory. So one can define associated tooth coupling as a ratio of n and k, and consider the corresponding tooth limit. For k greater than 2, the global symmetry is just OSP 6,4, which is superconformal symmetry in this case, and there is also extra U1 baryonic symmetry, under which fields in B fundamental representation acquire charge +1, and fields in anti-B fundamental representation acquire charge -1. However, in the rest of the talk, I'll consider operators which have 0 charge under this one U1 baryonic symmetry, so this will not be that important, and I will assume that the Chern-Simons level is greater than 2, so there are no supersymmetry enhancements. So the dual gravitational description is in terms of M theory on ADS4S7 background. So this background can be thought of as a near horizon limit of M2 brane solution discovered by Duff and Stelle, which is just ADS4, well, the near horizon limit of this solution is ADS4S7, while the orbifold action can be easily understood in the Hopf vibration coordinates of S7. Well, in these coordinates, the angle along the Hopf fiber, well, here it is called phi, and the orbifold action is such that it is identified with the period 2 pi over k. So I can just reabsorb this k into the metric by rescaling this coordinate, so that the 7th part can be written in this way, where a is just one form on CP3 such that its differential is Cayley-form on CP3, and there is also non-zero Ramon-Ramon form such that F4 is proportional to the volume form on ADS. So one can consider also reduction to type 2A theory. This is done by taking the radius of this 11D circle to be small, and in this case, the type 2A theory is weakly coupled. The background is just ADS4 CP3, while the radius of ADS measured in string units is proportional to the square root of lambda. So then, if we consider M2 brane in this background, its effective tension then just proportional to square root of nk. So if we want to consider large tension limit, effective tension limit, we can fix k and consider n to be large. So then observables in this semi-classical M2 brane expansion will have the following form, where there is a classical piece, then there is one loop part and higher loops part in principle. So the key features is that we consider M2 branes which wrap a lambda-dimensional circle. This means that fluctuations on the surface can be expanded in Fourier modes with respect to this 11-dimensional circle. The topology of the M2 brane would be some 2-dimensional world sheet times a circle. So expansion in Fourier modes effectively introduces a tower of Kaluza-Klein modes on this world sheet. The masses of these Kaluza-Klein modes would be then just proportional to the Chern-Simons level k, and here L is just an integer labeling these Kaluza-Klein modes. If we want to take type 2A strength limit, we can set k also to be large, and in this case, we can just discard all Kaluza-Klein modes and obtain just like the fluctuations would be just the same as for type 2A, Green-Schwarz string, and the expansion can be done in terms of effective string tension now, which is, again, just proportional to the square root of lambda. So then the idea is that if you include these Kaluza-Klein modes, you will be able to get 1 over k corrections, which are the same as G-string corrections. And these Kaluza-Klein modes appear from M2 brane perspective. So the simplest, well, not the simplest, but one of the setups where this can be tested is the 1/2 BPS Wilson loop in ABJM. There is an exact form for Wilson loop from localization together with the Fermi-Gauss techniques so that the expectation value for Wilson loop can be expressed in terms of the Airy functions, and there is also 1/sin in front. So by fixing k and setting it to be greater than 2 and expanding this expression for large n, one can obtain just the following part. And here there is like exponent 1/sin, and then there are 1/√n terms. It is interesting that the same expression can be written in terms of effective string tension. And in this case, it obtains the following form. And it suggests interpretation that there is a classical M2 brane piece, then there is one loop factor, and then there are high loop corrections. And indeed, as was discussed in the paper by Giombi and Zeitlin, one can consider a classical M2 brane, which is ADS2 inside of ADS4, and it also wraps a Hopf circle of a 7. And one can reproduce both the classical part and one loop term by considering this M2 brane. So the classical piece is given just by the wall volume of this M2 brane upon regularization of ADS2 volume by -2 pi, which is a standard thing. And masses for fluctuations which appear, well, Kaluza-Klein masses, can be written in this way. There are two modes for bosons which come from directions orthogonal to ADS2 inside of ADS4, where L equals to 0, these are just two ADS modes with mass squared equals to 2, while the shift appeared due to interaction with the Ramon form, and this interaction is non-zero only if you include the non-zero Kaluza-Klein level. Similarly, there are 6 modes which correspond to the directions in CP3. As one may expect, when L equals to 0, these are 6 massless modes, but they also are getting shifted for M2 brane due to non-trivial connection in the normal bundle. So similarly, one can obtain masses for fermions, and it is interesting to note that they can be compiled into n=1 supermultiplets on ADS2. Well, they can be paired into n=1 supermultiplets on ADS2, and this seems to follow just from the fact that this M2 brane preserves part of the supersymmetry of the target space. So it is translated on the supersymmetry on the wall sheet. So then one can compute one loop determinant for fluctuations, for instance, by using spectral zeta function, and it just reproduces the following, the 1/sin term. So everything matches. So apply the same setup for non-BPS quantities. We follow the same steps. Namely, we consider M2 brane wrapping a Hopf circle. When we reduce this M2 brane to 2D wall sheet, we have some type 2A string, which is dual to an operator on the gauge side. And type 2A string and its semi-classical quantization reproduces the planar part, while including Kaluza-Klein modes on this M2 brane will give you non-planar corrections. So one of the simplest examples where it can be done is the so-called null cusp anomalous dimension. It can be defined in the following way. So we consider a twist tool operator with large Lorentz spin, and in this case, the anomalous dimension grows logarithmically with the Lorentz spin, and the function which appears in front is what we refer to as the cusp anomaly. Just maybe as a comment, like as was mentioned in the previous talk, you can define null cusp anomaly in terms of the Wilson loop with null cusp, but these two definitions are just related to each other. So the planar part is controlled by integrability, and for instance, with Wick and Strock coupling, it can be expressed in terms of interpolating function in BGM, which appears in the Magnon dispersion relation. It is also interesting to note that the cusp anomaly in ABJM can be related to the one in n=4 sepangmils by the following identification of the parameters. And the interpolation function itself was proposed to have the following exact form by comparison of 1/6 BPS Wilson loop, for which the expression is known from localization also, and the slope function. So at strong coupling, the interpolating function takes the following form, and the dual description in terms of the strings is the so-called infinite folded string. So this string is stretched along ADS direction of ADS4, and it also rotates at the S1 boundary of ADS. The analogous construction in terms of Gubser-Klebanov-Polyakov string in ADS5. So from string perspective, the cusp anomalous dimension was computed up to two-loop order, and the result just matches localization predictions. Here, k is the Catalan's constant. So to consider M2 brane, we just uplift the solution by wrapping M2 brane on the Hopf circle. In this case, the fluctuations, well, the classical energy would be just the same as for type 2a string, but the interesting question is, what do you get from one-loop expressions which contain these Kaluza-Klein modes and lead to non-planar corrections? So masses for fluctuations appear quite similar to those in the case of the Wilson loop, though the two bosonic masses are just a bit shifted due to rotation of the string. So then one can compute, since the string is infinite and the induced metric is flat, one can also expand the fluctuations in terms of the continuous momentum corresponding to this infinite direction. So to compute one-loop energy, one has to just take the integral of this continuous momentum and sum over Kaluza-Klein modes, which leads to the following expression for the cusp anomaly. So the second line from the bottom is just the planar part, which matches the type 2a string, and the bottom line is just what you get from including these Kaluza-Klein modes. And they contain 1 over like non-planar corrections due to this 1 over k squared appearing. So there is a generalization of the story if you consider the so-called generalized cusp anomalous dimension. On the string side, this corresponds to the same infinite folded string, but you can also add momentum to the string in CP3 direction. A convenient limit one can consider if one takes both spin and momentum to be large, but at the same time fixes the ratio of log S and J. In this case, the classical string or M2 brane energy can be written in this way, where there is extra dependence on this parameter x appearing. And again, the generalized cusp anomalous dimension is then defined just by the function which appears in front of this logarithm. So there is also relation to the n equals 4, to the string in ADS5 S5, where one can consider an analogous solution, and this relation can be expressed in this way. So the calculation in this case for a cusp anomaly is a bit more involved, as one has to, like the modes that you appear, you cannot obtain the masses for Kaluza-Klein modes explicitly, but you can do some tricks to obtain this expression in terms of x and the non-planar correction of this form. So another set of solutions one can consider is the so-called circular spinning strings. For instance, one can consider a string which has two momenta in CP3 directions. And in fact, there are physically two distinct types of this solution. The one is so-called fast string or long string. It is called so because it has a rigid size, and this size is independent of momenta of this string. So one can consider a limit when the momenta is large. And in this case, the classical piece together with one loop part from the string has the following form, where C1 is just some constant. And one can also consider one loop correction, and in this case, it also appears, the leading term appears as 1 over k squared. It is called so because it is stabilized by its own rotation. So when you set its momentum to 0, the string shrinks. So it's also reflected in the classical energy of this string, which has a similar form as in flat space. And for this solution, you can also consider a small, small momentum limit. And in fact, this solution wasn't discussed in the case of ABJM, but it was discussed in the case of ADS5 S5, and the one loop calculation that you can done, for instance, by considering M2 brane and discarding Kaluza-Klein momentum is similar to the ADS5S5 case. So then you can include, as I mentioned, Kaluza-Klein modes from this M2 brane and obtain the following non-planar correction. And what's interesting is that you can take the flat space limit for this solution, in which the string, or like the string becomes just a string rotating in two orthogonal planes, while M2 brane analog wraps some circle in the flat space. So in this case, you can see that there is a non-zero correction appearing, which can be interpreted as torus correction. And in fact, it's not surprising, as for such semi-classical states, one can compute two-point torus diagrams and obtain both real and imaginary corrections. Real part was computed for specific average states, so it's really hard to compare with this particular circular string. But one may expect an imaginary part in this case, and the imaginary part is responsible for the decay of such string. However, we do not see it here from this semi-classical approach, but it may appear from the resummation of higher loops. So, and similarly, one can consider circular spinning M2 branes, which have both momentum in CP3 and spin in EDS parts, and here is also the non-planar correction that we obtained from M2 brane. So maybe let me conclude. So in this talk, I have discussed how M2 brane, how you can go beyond supersymmetry observables by considering M2 brane, which generalizes string solutions. And this approach is based on the fact that there is a match between M2 branes and the results from localization, which appear for supersymmetric quantities. It is interesting to ask whether this match will follow if you consider higher loops corrections. For instance, for 1/2 BPS Wilson loop in ABJM, there is also, like, the expansion in terms of effective tension suggests that there should be a high loop, like two-loop term, which is non-zero. There has been also recent works by Gautoson and van Muyden, which suggests that, in fact, this higher loops term should disappear if you interpreted the semi-classical M2 brane partition function as something that gives you not expressions in the canonical ensemble, but in grand canonical ensemble in BGM, which is used in the Fermi-Gas approach. But a priori, it is unclear why it may happen here. So for n equals 4 subangles, you can ask the same question. Here I wrote down the expression, which is in fact valid in the planar limit when n is taken to be large, while for general lambda and n, it is in terms of, the expression is in terms of Laguerre polynomials. But anyway, you can still expand this expression for large lambda, which gives you effectively expansion in terms of the effective string tension. And you can ask whether you can obtain higher loops by considering type 2b string in the ADS5S5 background. So again, the first terms, like 1 over G string, can be interpreted as a disk partition function. There is a classical piece. This square root of effective string tension appears from regularization of determinants. But then there should be some higher loop term appearing from semi-classical type 2 base string. So this is all part of the future work. Okay, thank you.
Questions?
Hello? Yeah, take some time. So what was my question? Like, at which order mixing with double traces or triple traces will become important for this type of calculation?
At which order mixes with double traces or single traces? That's a good question, but I think at least the leading part would appear just from M2 brane calculation. It's really hard to say for me at which order you would pure mixing from other operators.
And then, so another question. So,
And it also happens at strong coupling. So I mean, I'm not sure where the.
But strong is probably when there will be like lots of stuff it mixes with, right?
Well, at least, again, the idea is the following. You have a match for supersymmetric quantities, like BPS Wilson loop of free energy. You can argue that this happens there just because of supersymmetry. But the idea is that M2 brane plays a more fundamental role, like the same role as type 2A string. So the idea is that you can consider the same semi-classical approach, and it, for some miraculous reason, also resounds higher genus corrections from type 2A string.
Just say for Kanish in n equals 4, right? If you look at the plot, then it's not even clear that 1 over n expansion at strong coupling makes sense. In a sense, there is a accumulation of singularities, right? Because each time it mixes with double trace, there is a pole in 1 over n squared term.
Well, yeah, I agree that this is subtle, but again, this is a result, again, not for n equals 4 sample mills. It's hard for me to say what will happen in this case because I don't have M2 brane description in n equals 4. But here, this is a ABJM case, so I again understand that there are less results known from the gauge theory, what will happen with anomalous dimensions. But again, this is something that can be done at ease in a way, and this gives you some predictions that, again, should be checked.
Then, like another question, so assume you consider general finite gap string solution. Then, in principle, obviously, classical spectrum is continuous, but it's quantized quasi-classically by imposing that like integrals around cuts, like filling fractions are integer, right? This results in a discrete spectrum in the classical limit. But now, when you add some corrections, probably you like break essentially integrability, then the question is whether this Born-Sommerfeld kind of quantization, which is based on classics, whether it should also receive some corrections on the right-hand side.
Yeah, I agree, and that's why one of the future goals is to consider higher loops just for BPS quantities to see if this approach can be, like, if this semi-classical approach holds for higher loop corrections.
About the first question, it's a question of which operator corresponds to that solution.
First question.
Legitimate question. First question was about mixing. So the claim is not that this classical solution corresponds to single trace, but to some particular
but you probably want to compute primary operator, right? Not a particular single trace.
About the second, semi-classical quantization will be exactly the same. It has nothing to do with integrability.
But integrability allows you to quantize this infinitely many of integrals around different cuts, but probably this disappears once you... Of course, like for folded string, there is only essentially one cut due to the symmetry, so it probably is fine. But if it's multi-gap solution, I don't know. There could be some subtle corrections on how like extra.
Wait.
Maybe you mentioned the beginning, but did you try also to look for this half BPS?
Sorry, can you speak a bit louder?
Sorry. Half BPS Wilson loop in 2,0.
Half
dimensional conformal field theory. Did you?
Half BPS Wilson loop in 2,0. That's a good question. I'm not sure whether this was computed from M2 brane, because in 60 2,0 M2 brane appears as contribution to giant gravity contribution to the superconformal index, and also as a conformal defect anomaly. But I'm not sure that the calculation is done for Wilson loop in this case.
Subleading term.
If you were looking at the one.
That would be an interesting question.
You mean like some, non-perturbative correction to the Wilson loop in terms of M2 branes? That's what you mean?
Yeah, because
yes, you can ask actually the same question not in 6D 2,0 theory, but in ABJM theory, because this expression For instance, in terms of the Airy function, it captures just perturbative corrections in 1 over n. So in principle, you may also have non-perturbative corrections the same way you have for free energy. In this case, you can also ask whether these non-perturbative corrections can be captured by some semi-classical M2 brane.
No, I guess the question is about 2,0, which is related to 5-dimensional.
Yeah.
Okay.
Yeah.
Because if you go to 5 dimension, then it's not conformal and
Okay, yeah.
it's more tricky.
Yeah, I see.
Okay.
Maybe one more question. Okay, if no further questions, let's thank Stefan again.
doesn't exactly fit in the topic of the conference. Maybe it's something in between the G and the S. It's something that has to do a little bit with the gauge theory and string theory, as you will see in a moment. And it's a work basically that appeared, well, 1 month ago, maybe, or something, with Miguel Correa and Alessandro Giorgudis, which are depicted in this picture here. And, OK, let me start. So let me remind you a little bit what are the various regimes in QCD which we love and we are interested in. So we have like 2 Mandelstam invariants which control the scattering processes in QCD. And we have this beautiful triangle which summarizes them all. So on the top, you have the asymptotic freedom regime, which is also the one that is closer to the topic of this conference, where S, the energy is very large, momentum transfer is very large, and we can use perturbative expansion, and we have a lot of tools. Then there is the regime in which S and T are order 1, where you have confinement, and where we have developed many techniques, like lattice QCD, now there is S-matrix bootstrap, and sometimes, since S and T are smaller than 4 pi something, you can think that it's small, and you can use some perturbation theory also. It's like a hard regime. But then there is in my opinion, the hardest regime of all, which is the one of four-dual scattering, or soft QCD regime, in which S is large, but T is small, order 1. And this is basically what I'm going to talk about. This will be the topic of my talk. So you see, it's like a little bit gauge, string, it's in the middle. Yes. OK, so the first and most important result in this regime that we can actually say it's rigorous from the quantum field theory point of view is the Froissart bound. And Froissart bound has something to do with the scattering of 2 particles. So you have 2 particles that go into 2 particles. You take the final momenta to be equal to the initial momenta. And then by the optical theorem, you all know that if I take the imaginary part of this process, this is proportional to the sum of the probabilities for 2 particles going into any number of particles. So it's like a bit far from integrability, but still. This is like what the imaginary part gives. And so you can already see that if you want to define the total cross-section, which sums up all the possible processes that can happen in a theory, you will have to take the imaginary part. And indeed, the total cross-section is just defined as the imaginary part at t equal to 0, because I set the initial particle, the final particle to be initial particle, so momentum transfer is 0. And you take the imaginary part, you divide by the flux of incident particle, and this beautiful bound that just depends on the axiom of quantum field theory tells you that this quantity, asymptotically when S goes to infinity, is smaller or equal than some log. So there is this log square, where the 2 is because we are in 4 dimensions. The 4 pi, you can define it in many different ways, but I like to think as the strong couplings in the effective field theory. And then there is a T0, which is a scale that gives the correct dimension to the cross-section. So it's a famous Froissart bound, which often people call it Froissart-Martin bound, because it was like rigorously proven by Martin years later using only the axiomatic framework of quantum field theory. And OK, this is like a beautiful result that stands since the 61. So in this talk, we basically challenge the result, and we try to go a little bit beyond, but this will come later. And T0, if you want, it's like 4m squared, which is the 2-particle threshold, if there are no spin-2 bound states around. OK, now let me remind you a little bit why Regge theory was so successful. So why like experimentally, basically successful. So you see, like this has something to do with the discovery of spin J particles. So if you have in a theory spin J that you can exchange spin J particles, then in the T channel, your amplitude will grow like S to the J. And this will immediately violate the Froissart bound that I just showed you. So the solution that was put forward by these people back in the days for the Regge theory was to take J and make it a function of T. So in this way, if J is a function of T, at T equal to 0, you can run it to a value which is compatible with Frossard bound, and everything is fine. Okay, so you go to like S infinity fixed, and the amplitude behaves like this. And indeed, basically what Regge theory tells you is that this exponent is basically given by this Regge trajectory, where here you can put all the all the resonances in QCD on a line, and okay, it's almost a line. I think it's curved, but okay, it's like a line. And it has some intercept. And then you see that immediately the Regge theory would give you some prediction for how the amplitude should grow. And then basically the first result that make Regge theory successful was the fact that if you look at proton-proton, antiproton total cross-section, it decays a little bit. This is just because I'm reminding you the cross-section goes like alpha t minus 1. So if the intercept is 0.55, this thing should decay. So this was a success of Regge theory. But then, already in the 70s, people discovered that the total cross-section should actually grow. It grows slowly, but grows. And if it grows, then it means there must be some other trajectory dominating. And this is the Pomeron, what people named the Pomeron back in the days. No? So there's some Pomeron trajectory that should intercept around 1 here. But what are the evidences for the Pomeron? So one experimental evidence of the Pomeron is this concept that I didn't know about before starting this project, which is the shrinkage of the diffractive cone. They call it experimentalist. So it's just a simple fact. You plug S to the alpha of t into the differential cross-section formula. So d sigma elastic in the t, just the amplitude square divided by square, the symbol ratio. You plug this formula, and immediately you see that this behaves like an exponential of t. So shrinkage is because as a function of t, this cone just becomes, decays exponentially. And then as function of s also should shrink because there is some log dependence in this coefficient. And the rate at which it shrinks, it depends on the slope of the Pomeron trajectory. So this was like one sharp prediction of this picture. And then indeed, already long time ago and then more recently, people saw this exponential decay in t, and they could even measure from this difference the alpha prime p, which suggests that indeed there is a flat trajectory that dominates this cross-section at high energy. And well, today, I mean, this is like some update. There are also like signs of deviations from this logarithmic shrinkage. So, and this is something that will come up later in the talk also. So, but this is like the experiment of the Pomeron. But when you look at this picture, at least when we started to look at this picture in detail, we saw that everything fit in a beautiful, let's say, logic. But actually, if you look at the details, there are some things that are still not satisfying from a theoretical point of view. And here I'm naming a few, which are the few that we could address in this work. So one thing is like maybe the most obvious, but still it's something not clear in the literature, is the tension between the Frossard bound and this alpha p, which is 1.08. So there is number 1.08, but alpha 0 should be 1 according to Frossard bound. So there is some tension. Then there is a clear experimental gap between the bound that, for instance, has been measured at LHC, which is like order 0.27 millibar, and actually the bound that you get from Frossard. There is this huge factor, so it's like a big difference. And then, more formally, the total cross-section at fixed S, if you maximize it, goes to infinity, because the amplitude is a distribution on the real axis, not a function. So it can diverge logarithmically. There is no problem with unitarity. And then, there is some hidden result, actually, from Oeme, a theorem by Oeme already in the 70s, that says that the Frossard growth is incompatible with the linear trajectories. So if you trajectory with linear slope, this is incompatible with the log square. And this is like an old result. So you see, then you start to have claims like perhaps 14 TV is not asymptotic, perhaps Frossard band is not optimal, what is as not in the, in the normalization of the log, these formal people that care about distributions, who cares? And then OMA proposal, nobody knows what it is, but it was already proposed that like some square root of t slope or something. So basically what I will do in this talk is to address these 4 points and try to make these blue statements a little bit more systematic. So this is the plan of the talk. Okay, so now let me give you some, basically already some summary of the main results that right away answer these questions, just to give you an idea. So one first main result is that, okay, we get rid of point like, we don't like distributions, we like functions, we like to smear distributions against some proper test functions, and we took this proposal already put forward in the 70s and revisited by Zibedov in the 2020s, or something, and we basically, what we did, we took the absolute, well, the total cross-section, and we average it with some function. Well, you can use many different functions with some, the shape of this kernel is for technical reasons. And we put an absolute bound, and this is what I will discuss in this talk, at each value of the energy. So it's a bound that you can take the experimental data, you can smear them too, and you can put these two plots on top of each other, and you can say, okay, this region here is clearly excluded. And this is something that has never done before. So we get this exclusion bound, which is analytic, actually. Well, it blends analytic and numerics, and I will show you in a few slides. And we could compare with proton-proton. But let me make a disclaimer, just for the, just to be fair, that I will consider only scattering of scalars. Protons are fermions, so they have spin. And I will assume that to show, basically, to make sense of this plot, you have to think that spin effects decouple at large energy, pion exchange perhaps is irrelevant. And if you believe all these things, then we get a bound which is order 10 from the proton-proton cross-section. Okay, so we got, like, instead of factor 100, a factor 10. But this you might complain because of all these assumptions. And then the other thing, of course, that we clearly see, because we have the analytic expression, we can see that the log square asymptotic is not reached at 14 TeV, basically. So it's clearly not asymptotic. So it's like just an outcome of this analysis. Then the second main result is that with the bootstrap, with the numerical bootstrap, we can reconstruct the function that we believe is the one that maximizes the interaction strength. And I will bring some argument, let's say, it's a conjecture, I don't have a proof, of course, that the amplitude that maximizes the interaction strength at basically at all scales sits at a special corner in a kink. And this kink is basically in the space of, let's say, the first two couplings that appear at lower energy in an amplitude, which is lambda phi to the 4 in a scalar amplitude, and d4 phi to the 4. So with the bootstrap, we have this allowed region, which is here. You have free theory down here. You have some special points. And the amplitude that we believe saturates the non-perturbative version of Froissart bound sits at this corner here. And you get this kind of shapes. So you see, it's like a very complex function, which has like peaks, dips, and different colors are the spin decomposition. So it's like a lot of structure that I won't discuss in detail. But this is the amplitude we construct. We call it the Froissart amplitude. And this will basically teach us something about this bound. In particular, that the black disk picture, which is the one that you imagine when you smash particle at high energy, is not the correct picture. There is another picture. So this will be the, this will be the result. Okay. So now let me explain you in 2 slides what is the asymmetric bootstrap. Maybe there are people that already know this, so sorry if I have to repeat myself, but let me give you a different perspective on the asymmetric bootstrap, which is that now we think of it as a more effective asymmetrics approach, in a sense that what we do at the end of the day is that we construct the most general function satisfying analyticity, crossing, and unitarity. And this, if you think about it, it's not that crazy as an approach, because in effective field theory, this is very standard. In effective field theory, you write a Lagrangian, which is your tool to parameterize all possible interaction compatible with the symmetry. Then you use perturbation theory to get consistent answers. And in this effective S-matrix approach, we write an ansatz, and then we use optimization theory to get answers. So it's like a non-perturbative version of effective field theory that has like good and bad things. The bad thing is non-systematic, as you can imagine, because I write an ansatz, optimization theory, what it means. We also don't know what it means exactly. So it's not systematic. But it's hard to include multi-particle. unless like there was like a recent attempt by me, Alessandro, and Pedro recently, but there was basically no non-perturbative multi-particle bootstrap, so it's very hard. But the good thing is that no perturbative, so it's ideal for strongly coupled systems, QCD, and integrable models in 2 dimensions, for instance. So that's what it's very good. Now let me tell you how it works in one slide. So we call it, this is like the primal strategy. We have many different strategies because it's an optimization problem. We can solve it in many different ways, less or more rigorous. One strategy is the primal. So consider the theory of a gapped scalar in 4 dimensions with mass m equals to 1. Then what we do, 3 steps. One step is to construct an ansatz, which I should not call it ansatz. I should call it, we expand the amplitude in a basis of functions. It's a Taylor expansion in a polydisk in this variable rho s, rho t, rho u. And since this variable depends on st and u, and these coefficients are permutation invariant, then this function is automatically crossing symmetric, and I sum up to n, let's say n terms in this basis expansion. Then this rho map is given by this Joukowsky function, which just maps the cut plane to the unit disk. And for instance, there is a parameter here which is not the same as not as the Frossard bound, it's another as not. Some arbitrary parameter for this conformal mapping that maps this point to the center of the disk. The cut goes, let's say, the upper part of the cut to the upper circle. And this ensures maximal analyticity for the amplitude, in the sense that this function clearly has cuts for all st and u, and it's analytic away from these cuts. Then we have to, then this function is crossing an analytic, but it's not unitary. So what we need to do is that we need to project into partial wave. We have to diagonalize the angular momentum operator. So we go to partial wave, and then we just project the amplitude with some Legendre polynomial. And t, you make it a function of the scattering angle cos theta and the energy in the center of mass. There is some prefactor here, but it's like a partial S matrix. And then the third step, once you construct this linear functional of your ansatz, so you see one point to stress is that this function is linear in the alpha, this projection is linear, and therefore when we maximize any objective, which can be, for instance, the total cross-section or any observable you want, with these constraints that the probability is conserved, it is just quadratic. And it's a good thing because we can solve it using semi-definite programming. And what we do is that we relax in a 2x2 matrix, and then we impose this constraint. So you see, it's a constraint optimization problem. You maximize something given some constraints. And then we use a grid for any energy greater than the 2-particle threshold, and then for any spin. And then, of course, the tricky part, which is the one that I will put under the rug, is that we have to take limits. And it took us years to make this limit under control. It was not easy, but now we can take n to infinity reasonably, L to infinity much easier, and the grid, we can make it very dense. So in this way, all these asymptotic limits that make sure that this function is very generic are satisfied. But this is like a numerical procedure that we have to follow. Okay, so this is the strategy for the bootstrap. And now, now let me go to the main goal of the talk, which is to bound the cross-section. So now the observable that I'm going to bound is the cross-section, but I will first discuss the analytic bound. Well, semi-analytic bound. So, yeah, I wrote it in d dimensions, it's not important. Put d equals to 4 here, it's fine. So we take this smeared cross-section that we want to bound at each s, where s is the extremum of integration. So we smear it from 4 up to s. I want to bound this function of s. The first step is very simple. We expand in partial waves, and then we split the sum. And this is the trick that has been used already in the past forever. So you basically expand. You expand in spin. There will be some, the S matrix will appear now in the expansion. And you have like low spin and high spin, and we want to bound separately low and high spin. Then for the low spin, we use unitarity. And unitarity just tells that 1 minus the real part of a probability is smaller or equal than 2. And we plug it here. And then if you plug it, you do this sum from 0 to L minus 2, you get some Pochhammer. And this gives you a bound on the low spin part. So it's just pure unitary, just bound smaller or equal than 2, which goes like L squared in equals to 4. But then the hard part is this high spin part. And for this, what we will do is that we will recast this asymptotic sum into a bound on some other observable. And this other observable, for some technical reason that I'm not going to explain, it's just the second derivative of the amplitude at some point. And this point, it's any point in the Euclidean region of the amplitude, so below threshold. Why this is nice? Because this quantity is dispersive, so it's this C2 that depends on some value of t of momentum transfer is given by an integral of the imaginary part, which is positive. Then you can expand also this integral, and you can basically put an inequality by restricting the integration range and by restricting the sum. So instead of start from 0, start from L. Instead of integrate to infinity, you integrate up to S. This gives you an inequality that involves the sum of high spin times some trivial kernel, and we use basically the bound on this C2 to put the bound on this high spin part. That's it, use just an inequality. So all in all, what we get is that we get an analytic expression which is valid for any dimension, for any value of the spin, and for any momentum transfer with arbitrary parameters. These are arbitrary parameters in principle, and depends on a data which you don't know how to bound analytically, but you have to bound numerically, and that's where we use the S matrix bootstrap. So we bound this C2 of T naught, and this is the results. So for instance, these are different values of n, the number of terms in the basis, and then you extrapolate n to infinity, you get the black curve, which is pretty close to the last point we have. So it's the maximum. You plug it here, and then you can minimize numerically with respect to spin and T naught. So you get the best bound. You can massage this expression, get something. So this is the result. And then one thing that you can do is that you can take S to infinity, and then you can check that if you take the saddle point, this expression becomes the Froissart bound in the dimensions, if you want. So it's like a consistency check. So this was the result that we obtained. And again, it's a bound on the smeared cross-section. It's valid at any energy, and it's rigorous, let's say. So let me go to the end of the talk already. So let me know what we did is that, we put analytic bound, and we checked that the analytic bound receives sizable correction 14 TeV, so we are not asymptotic at LHC. We put bound at any S on a properly smeared observable, but is it optimal? What about Oeme's theorem that I mentioned, the fact that the trajectory should have like square roots and not linear? These are the other questions. So let me say something about this. So about the optimality, what we did is that we maximized the smeared cross-section numerically this time. So before was an analytic bound that used some numerical input. Now it's direct numerical optimization, which is super hard, because you have to do for each S. It's not analytic in S, the expression. And we get these points, we can extrapolate, so we get all this region is included, all this region was excluded. And the good news is that we get a factor 5 improvement, so now we are just a factor 2 from proton-proton scattering, so we did a lot of mileage. And it grows slightly with S. I mean, you can barely see here because it's very hard numeric, but okay, we believe it grows slightly with S. And then what we can do? Well, now what we can do is that for each value of S, so for each value of where we maximize the total cross-section, we can construct an amplitude that saturates this bound. And then you can ask, what is the limit when S goes to infinity of this sequence of function? Does it go to a crazy function? Is it a nice function? What it is? And this would correspond to the strongest interacting amplitude, because you are basically maximizing total cross-section smeared all the way to infinity. And the way we argue, well, various ways to argue it, but the way we argue is that we plot the S matrix data for each value of S, and we see the movie. And the movie suggests that it goes to the king. We have other reasons to say it, but well, this is like one piece of evidence that if you increase the value of S, or if you smear at higher energy, these points move to the king. So now let me make a jump. Let me just assume that this is the amplitude that saturates the growth at any S, and let me see what happens. So the first beautiful thing that we see is that we see a discrepancy with the black disk. Because I told you the model behind Froissart wants a black disk, But instead, if we go to the impact parameter, so this, if you want, it's like some, perfect. It's really some picture of the sky that basically black, it means just the light was transmitted, and white was just completely reflected. And this is a function of energy, a function of impact parameter. So you see that there is some localized structure. An impact parameter, right, it's like a circular thing, so this looks like a ring. So basically this makes our conjecture that actually the ring model is the one that rules all the cross sections. Okay, so it's like there's some ring, it's not the disk. So we call it white ring because it's white, it's not black. And one thing you can do is that you can take this model, which is very simple, 1 minus 2 theta, heaviside theta, in some region. You can plug it into the impact parameter formula and get some expression which is difference of two Bessel functions. And now you can check whether this model, inspired by numerical bootstrap, matches the behavior of the diffractive cone that I mentioned at the beginning. So we have white ring, we don't have a Pomeron. So we can basically do the following. We take our numerical bootstrap. Basically, this is the differential cross-section for the Frossard amplitude. So that the amplitude we believe saturates the Frossard bound. It has some behavior, and it looks like linear Pomeron for small t. So we are happy because it looks like this picture. It reminds us QCD. Of course, we are very far from QCD. But then the beautiful thing is that this white ring model predicts more than the linear Pomeron that just goes exponentially down. It predicts that there should be some rings, because it's like a Fraunhofer diffraction. There are like some peak and some rings. And indeed, our numerics, which doesn't know anything about rings and models, it's like numerical result, it has these rings and this fluctuation. And this function, the dotted function, is our prediction using this model. So this model seems to capture qualitative the features that you see non-perturbatively. And then, just to give you some formula and connect to the old OMA theorem, this white ring model, of course, is compatible with Frossard growth in the sense that sigma tot goes like 4 pi the external radius square. And if the external radius grows logarithmically, you get logarithm square, so this is very simple. But then we can do the following. We can take, since we have an analytic expression, we can look for singularities, and we have this function that's like just a Bessel function when our model, when you go s goes to infinity. We take Sommerfeld-Watson, solve this equation, this integral is to be this function, and get that partial way for this model have a branch cut. So it's like a Regge branch cut, it's not a Regge pole. And so this is basically, if you expand close to small t, you get 1 plus square root of t. So this model is also satisfies the OMA theorem. So we are happy. And now, just before concluding, the last slide, let me show you the spectrum. So we have a function, analytic function. We can look at the spectrum, and we observe a lot of Regge trajectories. So this is like basically the full picture of the spectrum. So in 2 words, we see, for instance, on the right, you see what you would see the usual Regge trajectory in the Chufrauchi plot that look, well, they are like a bit square root log-like, but not really linear. But you have this trajectory on the right. And then surprisingly, you have also trajectory on the left. And you have many trajectories with infinite slope on the left, which is this OMA hallucination. And then you also have that there is a trajectory that has an intercept close to 1, again, not 1, so we don't really know what it means this, but looks like a Pomeron. And so this is basically the status. We have a function that achieves all these properties, and it has a crazy spectrum which we don't understand yet what it means, if it's necessary or if it's just a numerical coincidence. So to conclude, what we did is that put absolute bound on the cross-section at finite energy. Then the amplitude achieves the maximal growth, we believe it's at a kink. And then the Frossard amplitude has this rich nonlinear spectrum that we don't know what it means if it's necessary. And in the future, we want to scatter fermions, say, because we saw that this ring structure that we see in our numerical games is some ring structure that you also see at LHC. So it's something also that proton-proton has to do, and we don't know why. They have to have these rings. And, I leave you with this quote from from Frauci, actually, that I find very instructive about linear and nonlinear trajectories. And I'll stop here.
Questions?
Hello. Very nice talk, Andrea. Thanks. I haven't looked in about 20 years in this FRASA picture, so I don't know what happened in the meantime. But at the time, there was a sort of transition in what people in the particle data group were thinking is happening with the total cross section. So before about 2003, I think people were fitting so you showed the plot for the cross section that goes something like this. So they were fitting the first part with a small power law, S to the epsilon, that was called soft Pomeron. And then afterwards with the FRASA bound with a pi over m pi squared, which is 60 millibarns, the thing that truly appears in the FRASA-Martin bound.
Yeah.
However, afterwards, people started ignoring this, and they just started fitting with pi over m glue ball squared, which is much smaller, and then they would put S0 at the beginning instead of at the end. So let me see if I understood what you're saying, that you're saying that it's really pi over m pi squared, but moreover, you haven't reached the asymptotic limit yet until 14 TeV. Is that a fair statement?
Okay, this is like, thanks for the question. So let me clarify this. So we are not really doing proton-proton. So clearly we are doing some, right? So for us, there is no pi over m pion square. For us, there is pi over m proton square, like the glue ball of the people. But, you know, we are, post-grip of physicists, in the sense that we believe the scale of QCD is lambda QCD, not pion. So what we would like to do in the future is to do the correct bootstrap, including the anomalous threshold from the pion, and check that indeed this at high energy, large impact parameter gives like a small contribution. So for us, you know, we have some belief, but no clear proof. So this is something we have to work on. And this is basically the reason why our coefficient is much closer to the data than the naive bound where you put the mass of the pion. But this is the...
Yeah, what I was also wondering about the specific fit, because I don't know what happened in the meantime. But what I was confused at the time is why they changed to pi over m glue ball squared when they kept saying, oh, the fit is better, but it was actually 3% better in chi squared. So I was like, well, that's not a good answer. So so you would say that now the fit is much better in this?
No. I mean, from what we looked in some detail, and this fit is super hard. I have no idea how they imagine to get like numbers. It's very hard. And what we see clearly here is that we have an analytic expression that we can compare with asymptotic expansion, and log square alone, it's far from being the only contribution at 14 TeV. That's what we observe. So doing these fits is an art, and yeah.
Good, I understand, thanks.
On the previous slide, is it possible to determine not Pomeron, but the Oderon trajectory?
Very good, yes, but not in this setup, because we have only identical scalars. So for the Oderon, we would need at least like non-identical scalars, at least. But that's something we want to do. It's in this scatter fermions or something closer to fermions outlook. But yeah, that would be amazing, actually, if you could see some Oderon emerging by unitarity.
Thank you.
So a bit more naive question. So how do you see all these rings from these deeps on your plot? What's going on?
How you see the ring?
Well, you always like ring, and then show some picture with a couple of...
No, but this is very hard. I mean, no, because you see, the ring is the impact parameter picture. So you have like some, you have like some impact parameter picture that suggests there is a ring. Then you check the consequences, and the ring describes qualitative, some differential cross-section and high energy. But then the range trajectories you are talking about are basically the peaks in this ring structure. And that we don't know how to, we actually don't know how to relate it to the ring, because the ring is very naive, doesn't have crossing. I mean, not even unitarity, it's really just impact parameter representation of some simple function. And we don't even have the nice square root branch part, because you see this trajectory curves but doesn't touch. And then on the left, you have like many square root trajectories. So probably the ring itself, it captures some physics in some regime, but it's the correct picture that describes this amplitude is very different. And we should add more, we should have like some function that gives like more trajectories, more with the infinite slope, let's say. And this is something that actually, we only know one paper about this, which was by Schwarz before he moved to string theory. So we like to call them Schwarzian trajectories. So someone thought about them.
So in this weird trajectories, is there any evidence or any, anything observed on these trajectories?
It's, we only have bootstrap, no, we have only bootstrap evidence, because in all the non-perturbative amplitudes we construct, these trajectories seem to be there. So for us, it's a suggestion that perhaps are really something necessary for crossing. But it's non-perturbative, we don't know. Absorbing? Observing. Sorry, I thought absorbing. What are you going to absorb? No, no, and these are, no. These are impossible to observe directly. But many stuff are impossible to observe. I mean, you will be surprised how many things you cannot observe experimentally. I mean, let me give you just one, what is the plot? This one. You see, this is the total cross-section. So you have the peaks, that's the stuff you see. But then the other part on the subleading trajectories are these dips. So you will not going to see them if you just fit with Breit-Wigner. It's very hard.
Do you have some idea how this black ring picture could be explained from the old Parton picture? Do you have some physical idea what happens inside the hadrons?
Yeah, it's something that people are debating. Maybe I have some, let me go to the backup slides. Question. Yeah, so actually at proton-proton scattering, people observe something they call hollowness effect. They call this hollowness effect in the sense that the inelastic cross-section has a hollow, you see, has some small hollow at small impact parameter. So only like I have some image in which like you have this, basically these particles, if they smash up front, somehow they will just bounce back. Instead, if I smash them with some impact parameter, it's more likely they will fragment, let's say. But yeah, this is like people are trying to explain this kind of plots, and it's very hard. But they are trying with the Parton model, but I'm not an expert.
Okay, then I guess we need to finish. So let's thank
thanks
again.
Now it's work? Yeah, no, it works. All right. So, first of all, thanks to the organizer for inviting me to speak here in this very nice venue at this very nice conference. So I'm going to talk to you about a recent paper that I'm going to talk about work that I've recently done in collaboration with Federico Ambrosino and that I am currently doing with Federico, Matte, Lenses, and also with Roberto Tateo. And just to give you the references, this is the main article I'm going to be talking about, but also I will mention things about recent work in progress with the people that are listed here. Okay, so let me start with a brief slide on motivations. So as you might know if you saw a previous talk of mine, I am primarily interested in understanding the space of two-dimensional quantum field theories. And in particular, using the ERG setup, which identifies fixed point as conformal field theories, and then studying the flows between them, from them, then going somewhere. And in this setup, symmetries are really important as they seem to be everywhere, essentially. In particular, in this ERG setup, they act by reducing the infinite dimensionality of the setup. So if you keep on having some kind of infinite space of possible theories, but if you have symmetries in the game, then you can reduce the amount of infinity, in a sense, that you're dealing with, right? Because you want to have theories that respect a certain set of symmetries, so you have to reduce the possible interactions and so on. So that's one naive way in which symmetries are important. But maybe more importantly, they impose selection rules, things like Toft anomaly, matching, and things of the sort. And if you're lucky enough to have enough symmetries, sometimes they allow you to control the flow, and that's what happens when you have integrability in the game, right? So these are just a few examples of why symmetries are important. And so this is a picture that you probably have already seen. So I just made it smaller, so it's less boring. But we have three principal types of flows that we can have in this ERG setup. So we have marginal flows that go from a CFT to another CFT. If you're lucky enough to have a marginal operator, then there is a conformal manifold, and you can use the coupling to that operator to move on the manifold. You have relevant massive flows. So you have flows that start on a UV-CFT, you have a relevant operator, and then you turn on the ERG machinery, and then this flow usually goes to an empty theory. If you have a mass gap, then the degrees of freedom decouple in the IR, and then you end up with a theory that doesn't have any propagating degrees of freedom. It might have some topological features, but in general, it's an empty theory. And then you also have my favorite flows, the irrelevant flows, which actually are the majority of the possible flows if you're in dimension bigger than 1. So you have an irrelevant operator that you can use to perturb a conformal field theory. Now you cannot think of that as a UV point anymore because of how ERG works. But if you insist on following the direction of a specific irrelevant operator, then you can actually try to trace a path in the space of theories, and this is the example of the TT-bar operator, which actually allows you to do it exactly, so you can actually flow that. But, so in a shocking twist, I'm not going to talk about the irrelevant operator, but I'm going to talk about the relevant flows, and in particular about massless flows. So we know, we have some examples, and I'm going to give them, that there exist flows in which the mass gap is 0, right? So when you take a UV-CFT and you perturb it in a certain way, some degrees of freedom survives in the IR. So what happens is that in the IR, you expect to have another fixed point, and that fixed point is a CFT because it has propagating degrees of freedom. It's not an empty theory. Okay. So let me review what we know in 2 dimensions. I didn't mention, I will be focusing on 2 dimension. So in 2 dimension, we know some example of massless flow. Probably the most famous one is what is sometimes called imaginary mass Sine-Gordon theory. So you have an action, the Sine-Gordon action, And Fendley, Salor, and Zamolodchikov, and also Alyosha by itself later, they studied the regime where mu, here I put a square root in the coupling, when mu is less than 0, then this coupling becomes imaginary. And in this article, they showed that the beta function is compatible with a massless flow, so a theory that flows to an IR fixed point. While, well, very famously, if mu is bigger than 0, then you get a massive flow, and the theory flows to an empty fixed point. And this theory, you can also perform quantum reduction on the quantum algebra that underlies Stein-Gordon, and you can produce the phi-13 massless flows that go from MQ plus IQ through the field to the relevant field phi-13. So the most famous one is the tricriticalizing to Ising flow, which is obtained putting I equal 1 and Q equal 4. I'm going to review also the notation here, but this M just simply means minimal model with P and Q as written here. So this is an example, but we have other examples. And Doridan and Tateo in 2000, they showed that you can define, well, you can control using integrability these two types of flows. So flows that are issued by the field phi-15 and by the field phi-12, and they interpolate between these these classes of minimal models in this way. And one thing that, so what the method that they used, they started from the ODIM correspondence. So they had some information on the massive version of these flows, and then they conjectured a Destri-de Vega equation for that. They studied that, and they saw that it corresponds with previous conjectures on the existence of this flow. But the question remains that can we interpret them in the same way as for the imaginary mass Stein-Gordon as an imaginary mass version of the Gibber-Mikhailov-Shabat model, which essentially is the Bullock dot model, which has this action here. So can we use quantum reduction to construct this massless flow from this theory where mu is less than 0? This, as far as I know, is an open question. I might be wrong about that, but I didn't find any information on that. Well, we know that we can do quantum reduction on the version for mu bigger than 0. I'm talking about the imaginary mass version. Okay, so this is what is known from integrability, but recently there has been some interest in other types of flow. So Klebanov and collaborators, they were interested in studying these UV theory, M103, so this minimal model, perturbed by a field phi-17. Now, in principle, this field is not supposed to be, these theories, the formation is not supposed to be integrable. Okay? We can do some counting argument, and the counting argument is inconclusive. We cannot conclude that the theory is integrable. But nonetheless, they had some argument using some anomaly matching, saying that this flow, if it exists, it should flow to this minimal model M83. Okay, and then they extended the analysis, and they studied this class of model, this one-parameter family of models, also perturbed with phi-17, that it's supposed to flow to this IR here. And then even more recently, in 2024, slightly more recently than this one, Tanaka and Nakayama conjectured a two-parameter family of flows that now is generated by the field phi-1 to k plus 1, where k is an integer, but it can also be an alpha integer. There are some technicalities here that I'm not going to go into. So there seems to be a whole host of massless flows. But all of these flows are conjectured. There is no explicit proof of their existence. There are strong conjectures, but they're still conjectures. And so, well, mimicking what I said before, we can ask, do these arise from some kind of imaginary mass version of, this time, Liouville field theory? Because if we think about generalized minimal models, where we have Liouville theory that describes the UV theory, with some central charge that is dictated by the parameters of the system, if we do this interpretation of this action as being the UV theory, we can we can identify the field phi 1 to k plus 1 with this exponential here, where m is related to k by a linear relation. And the question then is, if I put mu less than 0, can I, by doing quantum reduction, reproduce these flows? But of course, I'm not going to answer to this question. This is a question that is out there, and I hope at some point we might be able to answer that. OK, so this is more or less what is known in 2D about massless flows between minimal models. One important thing that I want to stress is that this conjecture here, the conjecture of the existence of these flows by Tanaka and Nakayama, was done based on these flows preserving something which is called modular tensor categories, essentially these non-invertible symmetries that you might have heard about, and I'm going to review them in a moment. The idea is that these flow, this operator here, preserve a subclass of all the possible non-invertible symmetries in this theory, and you go and scan which are the IR, the possible IR that also have that category. And they identified these IR here. OK, so for this reason, let me just very briefly and very probably sloppily introduce you to generalized symmetries if you don't know them already. But the idea is actually pretty simple. So the idea is to go back to the definition of global symmetries. They are unitary operators. They act on a Hilbert space, which usually is defined by just slicing along a time direction, our space-time. So we fix t, and at each t we have operators that we have operators O, we have a Hilbert space, and then we have unitary operators that act on this Hilbert space. And the additional requirement for this to be global symmetry is that we want them to be conserved on time. So we can move the time slice, we can move on the time slice, and the U will always be the same. Okay? It doesn't evolve in time. And also note that U acts on all space-time, all space points, sorry, and it's defined on this codimension 1 Cauchy slice. Okay? So the picture is somewhat something like that. You have an operator here, and then you can, since U is conserved in time, you can think of defining it on 2 time slices, which are far from that, and then you just sandwich it inside with the operator inside, and what you get out is a deformed operator. It can be a rotated operator, it can be another kind of operator, depending on the symmetry and on the operator you're considering. But the important thing is that you can, if you just move away from the idea of slicing along the time direction for a moment, you can think of this action as being essentially a codimension 1 surface that surrounds your operator and acts on that by this chain, by this chaining. Okay? So we can interpret this if the idea is that we move from some kind of space-time picture to a Euclidean point of view. Now all time and space are essentially on the same ground, and so we don't have a natural Cauchy, we don't necessarily have a natural Cauchy slicing. So it is more general to say that these operators are defined on a codimension 1 manifold, which can be general. The important thing is that they are conserved. So when we deform the manifold without intersecting any insertion in your space-time, they will be the same. They won't change. But now if we take this point of view, and this is meaningful because it reproduces the usual definition of global symmetries, we can actually generalize the definition. So we start from saying the standard global symmetry is topological because I can deform the surface, invertible because there exists an inverse, and codimension 1 operator. So operator defined on a codimension 1 surface. But we can think of dropping some of these assumptions, right? So we don't really want to drop the topological part because that's what makes the object a symmetry. But we can drop the invertibility condition, and this brings us to the non-invertible symmetries. So these are symmetries that do not necessarily have an inverse, and I'm going to give you an example later. Or we can drop the codimension 1, we can change it and actually consider operator defined on a higher codimension surface, and these are the higher form symmetries. Now in this talk I will be focusing on non-invertible symmetries specifically, and specifically in 2-dimensional conformal field theories. Okay. So let me give some notation for CFT. So all this is introduction notation and things like that, and I will give you some result later. So as I said before, this symbol denotes a minimal model. PQ are two integers, which are bigger or equal to 2, and I choose these ordering. So P is bigger than Q. That's not the usual one, but it's easier for me because well, there is no real reason. I can just rearrange them, and the formula will remain the same, and just need to switch the parameters. But this is the way that I chose it. And the central charge is, as you all know, this one. And in this minimal model, there exists P minus 1, Q minus 1 over 2 primaries. The primaries are denoted by phi rs. R goes from 1 to Q minus 1, S goes from 1 to P minus 1, and this is the conformal dimension. Okay, so this is all pretty familiar stuff. But an important thing is that all these primaries, they satisfy some kind of Verlinde algebra. Well, not some kind, the Verlinde algebra, which is not properly an algebra. It's more a fusion ring, really, because you don't have only one term here. You have a sum of terms, right? So the bracket here denotes conformal families. As you all know, you have a primary, you have all the descendants. Primary plus descendants is a conformal family, and it's denoted by a square bracket. Here, rho, sigma, and kappa are pair of indices, R and S. And when you do the OPE of two operators belonging to two conformal families, you will find out that you get a sum over operators of other conformal families with fixed coefficients, which are these curly n. Okay, so this is also well known, but it's important because this expression here has the same form of what you find when you study non-invertible symmetries. This is a fusion ring, which is the same mathematical structure. Okay, so one can think, and this was reviewed in this article, it was actually thought earlier than that, but this review is quite clear on the math that is going on. We can think of taking each family and associate with that a Verlinde line. So an operator defined on a line, which I call curly L rho, where rho is the subscript. And this line acts, like I said before, by chaining on operators in this way. So it acts on state on a cylinder. The state on a cylinder is generated. In this case, I use a primary, but I can also use a descendant. And then the action of L on this operator is just given by this line, which is just a factor of two modular S matrices. And the modular S matrices are objects that you can use to build this curly n, the Verlinde coefficients. Okay? They are tabulated, they are numbers. Nothing fancy. Okay. So this I can define this operator, and if I go and see what happens when I act successively with two operators, because of how are they defined, they satisfy the same algebra, the same Verlinde algebra that I showed you before. Or better to say, they satisfy a modular fusion category. Or they form a modular fusion category. Okay? So these lines are these non-invertible symmetry lines. And I'm going to show you in a very simple example that they really are non-invertible. Okay, in Ising model, you have this structure, and one of the lines is a non-invertible line. So the example, if you take Ising, how does it work? You have three primary fields, so you have three families. One is the identity, one is the spin, one is the energy. They have these dimensions here, as you all know. And then I take each one of them, and I associate a line with each one of them. One is the identity line. Sigma gets associated with the line D, which is the Kramer-Spanier line. And epsilon gets associated with eta, which is the energy line in a sense. And now if you go and check, if you take the big yellow book and check the Verlinde algebra for this case, you will see that the line behave like this. So eta contracts with itself in the identity. But importantly, this Kramer-Spanier line contracts with itself with the identity plus an energy line. So if you think a moment about what this says, it's saying that when you take an operator, any operator O, and you act on it with a line, with a Kramer-Spanier line, you will end up with an operator that has a tail. So you end up in a twisted Hilbert space. So what does this line is it maps local operators to disorder operators. That's what the Kramer-Spanier duality does in Ising, right? And the Kramer-Spanier duality in a CFT is really a symmetry of the system, because Kramer-Spanier maps the low temperature to high temperature Ising model, but if you are in a CFT, you're at a self-dual point, so that's a symmetry of the system, right? It's a weird symmetry, but it's still a symmetry. It's a non-invertible symmetry. Okay, so this is just one example. You can go and check your favorite minimal model. They will all of them, they will have these structures. And crucially, these structures are very, very much like a fingerprint. They are all different from one another. So they kind of identify the minimal model that you're looking at. And just for information, this is called the Z2 Tambara-Yamagami category. Okay, so just keep that in mind. I'm going to return that briefly in a moment. But let's return to what's the topic of the talk. We want to consider a relevant deformation of this form. So we have an action, a minimal model action, and we just perturb it with a relevant field, okay? With a coupling G. And now what we want this action to describe a flow that goes from a UV. We know that this describes the flow from a UV, because this is a relevant deformation, but we want that on top to go to an IR CFT, which is a non-trivial CFT. This is a massless flow. That's what we're searching for. And a few things to notice is that in this action, in this expression, there might be more relevant operators that appear. This is what Wilson tells us. We need to add all of the possible relevant operators and then check how they behave under the RG flow. So it might very well be that this is just a description, infinitesimal description out of the UV, but to actually get to the AR, I need other relevant operators to be added to the theory. And another thing which is important is that the effective central charge of the UV has to be bigger than the effective central charge in the IR. Now, it doesn't necessarily have to be monotone, because this is not the Zamolodchikov C function. It's a different function, but it equates Zamolodchikov C function in a CFT. So this means that it can oscillate, but in the UV it needs to be bigger than the IR. Or if you want, another way to say is that the number of degrees of freedom in the UV has to be bigger than the number of degrees of freedom in the IR. Okay? Good. So this is the way that I will denote it, very simply. MM with an arrow and phi. Okay, now take that, take the UV, and then suppose that in the UV, we choose the deforming field so that there are a set of lines, set of Verlinde lines that commute with that. So we choose, we just check which are the lines that commute with the flow. And suppose we find a bunch of them, and suppose and then finding a bunch of them, we collect them into a maximal set of lines that is also closed under fusion. So it's a subcategory, okay? We start from a larger category. Some of the lines will not commute. We select the maximal amount of line that closes under fusion, okay? Now, this object here, since all the line commutes with the deforming operator, it will be preserved along the flow, right? So we need to find this same category, this same subcategory in the IR. It can be a subcategory in the IR, so there can be an enhancement. We can have more lines in the IR, but this object C has to be contained inside the IR. Now, it turns out that this condition is incredibly constraining. And this is the procedure that was done by Tanaka and Nakayama that we sort of automatize in a sense. And essentially uniquely pin down the allowed IR. And in doing so, it uniquely pin down the possible massless flows, right? And also one thing to be noted is that this is not a positive statement, this is a negative one. So what this does, it prohibits a certain flow from existing because there is no matching between the modular categories, okay? But it doesn't actually tell you that the flow exists. The flow may exist. Now, you can say, okay, if a flow is allowed to exist and it doesn't exist, then you should give me some reason why it doesn't, right? There should be some reason why a flow that might exist doesn't. But still, I cannot claim that the flow that I am showing you, these ones, they actually exist. I'm just claiming that they might exist. So this is just to show you the complexity. We have very many, for example, flows that start from M7, 8, which is unitary. We have a lot of flows. These ones are the usual 513 flows, the one that go along this line. But then we have many other ones that are allowed to exist. Okay? Good. So this is the first part, and this is essentially what Tanaka and Nakayama did. Nothing new. Now, what's new, okay, I'm going to speed up slightly here, but what we found out is that there exists a description, an NLIE description, something like a DDV equation, that appears to encode the ground state energy of all the flows that I showed you before. This is, again, an assumption. I'm going to return to that later. But essentially, the idea, just to give you an idea of what NLIE is, for those who don't know, the NLIE is a way to encode the dependence of the energy, energy of a state on a cylinder, on the radius. Now, we know that the energy in these cases should have this limiting behavior. In the UV, it should go to the CUV minus 24H, where HS tells you which is the perturbing field, and the same thing should happen in the IR. We fix the mass scale. Well, I mean, this is all technical, but essentially these are the equations. So you have the energy is defined as some kind of integral of some functions, and these functions have to solve this coupled pair of equations. Okay, this is the massless version of the usual Destri-de-Vega equation, and this is the definition of L. Okay, this is just to just briefly show the type of equation we're dealing with. It's very similar to the TBA equation. It's a different approach, but it's a similar concept. And now the important thing is the data that we have here. The data consists of two contours in the complex plane, and these contours are the ones that tell you which is the state on the cylinder that we're looking at. In particular, for the ground state, these lines are just slightly above and slightly below the real line. So they are simple contours. If you consider excited state, they can be more complicated contours, but we will focus on those. And the rest of the data, it consists of a twist, which is a real number, and two kernels, phi and chi, that appear in the integral equation. Okay? And these determine the specific theory that we're dealing with, because these are the ones that constrain the UV CFT, the IR CFT, and the perturbing fields. And what we did was to conjecture to a two-parameter family of kernels, which are these ones. And I conjectured them following a number of arguments. I wanted them to be bounded. I wanted them to define functions and not distributions. I wanted them to have this cosh, because this cosh reproduces the bulk energy. So there are a number of assumptions that go into that. But crucially, I didn't assume them to reproduce the known kernels for the DDV for 515 or for 513. Okay? This is something that I found out later that it's the case. So that's an assumption. And when I have 2 plus 1 parameter, the two in the kernel and alpha, I can fix 3 quantities. So I can fix the UV and IR effective central charge in this way, and the deforming field in the UV. And this Z is just a 1 or 2, depending on the field being odd or even. It's just a quantity. It's nothing too fancy. So these 3 are input data. I start with a flow that I suppose might exist. I start from a UV, from a deforming field, and I say, okay, I have an IR. I fix these 3 quantities, and then as a check, I can go and see if HIR, which I can also compute from the DDV, does belong to the CATS table of the IR CFT. And this constrains the possible values of kappa and psi that I can have. And what I find is that I find some Diophantine constraint if I assume that Z is conserved along the line. This is the equation that I find. If I don't, it's slightly more complicated. But these constrain the possible pairs of UV and IR CFT that I can have. And what I find is that the Tanaka-Nakayama family is contained in that. And moreover, all the families of CFT that I find are the ones that we found with non-invertible symmetries. In particular, this is one example. So there seems to be something here, because I didn't input any information on non-invertible symmetries here. I just find the same exact set of flows that I would find using non-invertible symmetries. And additionally, one other thing that we find is that if we do numerical analysis, we find that the theory really doesn't only contain the first relevant operator, the one that is dictated by this dimension here. So this is a fixed one. This is the most relevant operator that appears in the UV. But as I said before, there might be subleading terms. And numerical analysis tells us that we should really add also these two. For example, in 517, we should also add these two. And if we go and look at the commutation of these fields with the non-invertible line, we find that all three, if I choose the lines as the one commuting with 517, then 515 and 513 also commute with all those lines. So they also are allowed on the flow. You can have them because they don't break the non-invertible symmetry. So this is also another non-trivial check that something is going on. And this is an example of the numerics that we did. One thing that I should say, the numeric is kind of low precision. It's enough to give us some confidence that this fit tells us that we need 517 and 513. Here 515 has the same dimension of 517, so it doesn't explicitly appear. But this really suggests that since this line is much more precise than this one, you really have to include subleading terms, okay? Right. So one thing, I will conclude with that. One thing that is important to remark is that I am not claiming that the theories, these flows, are integrable. At the moment, I don't feel confident enough in saying that because on one side, we don't have precise enough numerics to do, for example, comparison with CPT. It's something that we're doing at the moment with Roberto. So I hope to be able to say something in the future about that. So I don't feel confident in saying that, also because there might be reason why this function is not exactly the ground state energy along the flow. It only flows to the exact energy in the CFT point. And that's because in the CFT, we recover integrability. So the idea, for example, if you think about it, if you think of the kernels as somehow having to do with the two-body scattering of some theory, if this theory is non-integrable, the two-body scattering is not the whole physics, right? You need to include higher particle scattering, particle production. So it might be the case, and this is a guess, that this encodes only the two-particle physics of some theory, and to have the actual ground state energy, you will need to include further terms. So this is just one way the things could go to sort of, okay, well, this is something that might be, and you can ask about that. But this is a list of things that we want to do. This is a short list of things we want to do, and yeah, so thank you very much.
So before question, because people may start dissipating, so according to Google, there is some kind of sun outside, so we'll be taking a group picture outside right after the questions. Don't run away.
Questions?
Would it be interesting to study the RG flows between minimum models with additional W symmetry?
Oh, yeah. In principle, you can. And I think you would have to consider not just one equation for the DDV, but more than one. Like when you consider, in a massive case, when you consider AN structures, you will get N DDV equations, and they will have a central charge which is larger than 1, so you can identify them with this W symmetry thing. So yeah, I think it's possible. It's just, I mean, we have a lot of problems with this already, so yeah, and that's in the future.
More questions? Okay, let's thank Stefan again.
Okay, thank you.
Okay, so let's start. Welcome to our afternoon session. We will start with a talk by Frank Coronado from Zurich on bootstrapping the n=4 super Young-Mills correlators.
Thank you. Well, first I just want to thank the organizers for giving me this chance to present my work. Today I'm going to talk about this work we prepared with Simon, Ankoy, and Sarah about bootstrapping correlation functions in planar super Young-Mills. So super Young-Mills is our favorite theory because it's the simplest gauge theory in 4 dimensions, and due to its many symmetries, and especially in the planar limit, we believe it's solvable thanks to integrability and thanks to the big work of this IGST community. We now have managed to compute many observables, at least in the planar limit, where we have this integrability. Super Young-Mills also serves as a laboratory for testing non-perturbative techniques that have wider application, such as the conformal bootstrap. And in fact, there are some recent works on using conformal bootstrap at a finite number of colors by Shai. Also, in the recent years, there's been progress on combining this powerful conformal bootstrap technique and also the integrability of the planar limit to determine the OP data of line defect CFT embedded in super Young-Mills. And today, I'm going to follow this same philosophy of combining conformal bootstrap and integrability, but now I'm going to address OP coefficients of local operators. So the protagonist of today's presentation is going to be the scaling dimensions of the local operators, the OP coefficients, and also the 4-point function of a stress tensor that is dual to this string amplitude in ADS. Okay, so regarding the first set of data, the spectrum of scaling dimensions, that is a problem that it's solved. We can consider this to be solved in the planar limit. And that means that, for instance, we have complete control over the dimensions of single trace operators. And at any value of the coupling, non-perturbatively, we can compute, let's say, numerically, what is the value of the scaling dimension and how it evolves all the way from weak to strong coupling. This plot has many years already. And since then, there's been huge progress, also in part thanks to the great work by the group here at King's College, that now there is a bank of data for the spectrum of many of the non-protected operators. So this problem is solved. But now we would like to address the next set of OP data, which corresponds to OP coefficients. So here I'm going to consider the simplest OP coefficient. First, I start by considering the stress tensor multiplet. I consider the OPE of 2 stress tensor multiplets here. We pick our favorite component with this multiplet, which is this operator of dimension 2. And in the OPE, we have some singularities, which are controlled by some operators and their OP coefficients. For instance, here we have the stress tensor itself appearing in the OPE. And then we have other type of operators, which are non-protected, such as Konishi, which is a single trace operator, and then also these other type of non-protected operators, which are called double twist operators or double traces. If we were to address this problem at finite number of colors, we actually wouldn't be able to really distinguish between single and double traces. In fact, there will be a mixing, which we can maybe see in this figure where, let's say, we start on the free theory at g = 0, and start following Konishi, which starts its life with dimension 2. And then we start raising the coupling, and the dimension of Konishi also starts growing until it finds this operator that has dimension 4. And when that happens, there is some phenomena that is known as level repulsion, which is that there will be a mixing which will be resolved, and then these 2 trajectories are going to move away from each other. And the new operators on these outcoming curves are going to be actually admixtures of single and double traces. And this is going to keep happening as you keep making the coupling grow, and these dimensions also grow. We'll meet other double twist operators, and then we will have this complicated mixing as we move here in the coupling. But in this talk, I'm going to focus on the planar limit, a large number of colors. And in this case, we won't see the level repulsion. We will just have what we call level crossing, which is that now the single trace operator will stay as a single trace without mixing with the double traces. And here, this red line will represent the curve that Konishi follows untouched. So it's a smooth curve, and it just crosses the place where the double traces are. That is the plot for the scaling dimension. However, there is still evidence that this mixing would happen, and this evidence can be found at the level of the OP coefficient. This OP coefficient will have singularities exactly at those points where this mixing could happen. So it means that this OP coefficient is not such a nice quantity. It has some singularities. However, we know the position of those singularities, so we can multiply by some factor that removes them all. And also here, I'm also multiplying by the asymptotics, removing the asymptotics that we can learn from the strong coupling limit. And we define a much better behaved normalized OP coefficient. Now, what do we know about this OP coefficient? Actually, there are many results, perturbative results on the two corners of the coupling at weak and strong coupling. And from our definition and these results, we can see that our normalized OP coefficient should be some smooth curve that starts at 2 on the free theory, and then asymptotes to 1 as we go to strong coupling. Here, these curves correspond to the perturbative results, and of course, they are only to be trusted on the regime of validity, but then here in the middle, they just become pretty bad, and it would be nice to actually find what is the smooth curve, just like we did for Konishi in the past. So this would be something that we can call that we also are solving for the OP coefficients of the single trace operators. Of course, thanks to integrability, there are some methods, non-perturbative methods, that we can use, such as the hexagons or the separation of variables. And we already heard about the hexagons from Ben yesterday, and we will hear more about them from Alessandro in the next talk. And we will also hear from Carlos about this separation of variables on Friday. It is likely that in the near future, these techniques are going to be the ones that will allow us to find such a smooth curve and have complete control over this OP coefficient at finite coupling. But today, I will have a more modest goal. My goal will be to use conformal bootstrap to place bounds on this OP coefficient. So for a certain value of the coupling, I will try to find what would be the minimum value and maximum value that this OP coefficient can take, provided that it must satisfy some physical constraints. So what we will find here, interpolating between weak and strong coupling, will in fact be a band of allowed values. And the dream is that by pushing this program, we can eventually close this band and find the exact curve that interpolates. So that's the goal for today. And the method I will be using to achieve that is called the conformal bootstrap. And to introduce this method, I need to upgrade to a 4-point function, now a 4-point function of the 4 protected stress tensors. And I consider different OP channels that allow me to decompose this operator into a sum of infinite number of intermediate states. This is the S and T channel. And because the 4 operators are identical, then the intermediate states flowing are the same in both channels. So we have 2 types of decompositions that should be equivalent. And for instance, this decomposition would be a sum over all these intermediate states weighted by their OP coefficient times the conformal block that is fixed by conformal symmetry. And then we have another equality from this side, identical, but now with the conformal block in a different channel. And because these 2 must be the same, then we get an equation, which is an equation for the OP coefficients times these functions that are well known. And this equation should hold for any value of the cross ratios where this decomposition is convergent. And that means, in principle, we have an infinite number of equations, but also for an infinite number of unknowns. One of them will be Konishi, but also there will be other higher energy states that we also don't control. So the goal of conformal bootstrap is to take advantage of this equation to fix the OP coefficients. That would be the ultimate goal. But if not, maybe find a way to learn about them by maybe placing bounds on them. In order to do that, I introduced something that we call a functional in the space of cross ratios, let's say. So this just corresponds to some linear combinations of this difference of conformal blocks that appear on the crossing equation. And we use this linear combination picks certain pairs of cross ratios. In fact, this could be an infinite sum if we wish, but we will keep it to be finite. And we use this functional to rewrite the crossing equation as some sum rule. A sum rule that we organize as a contribution from the protected part, which are operators we know pretty well, and then the not protected part, which we don't know at all. And this equation is, well, the way it's given is like that the contribution from the protected part should be balanced by the high energy part that we don't know. Here we are also isolating Konishi and separating it from the other higher energy states, the ones with higher scaling dimension. Now imagine we were lucky and we are able to find these alpha k coefficients, just a finite number of them, such that we construct a functional that evaluates to 0 at all the states that have dimension higher than Konishi. If we were lucky and we find such a functional, then we wouldn't care what are these values of these OP coefficients, because this contribution will be 0, and then the OP coefficient of Konishi will be just determined by the evaluation of the functional on the protected operators, which we know pretty well. So that would be the ultimate goal, but of course that's a bit dreaming to be lucky and find such a linear combination that does that job. Something more modest than that would be to consider that let's try to find a linear combination that at each state above Konishi, it evaluates to something positive. And then given that this OP coefficient squared due to unitarity should be positive, then we can say that this quantity that we don't know is positive, and that should be balanced by this part here. Now, if we further demand some extremization of the evaluation of this linear combination on the protected part, then that will allow us to place bounds. And we also will normalize the action of this functional on Konishi to be +1 or -1, depending on whether we want to find an upper bound or a lower bound. So this would be the algorithm we will be following, trying to construct a functional, trying to find these coefficients, such that we construct a positive functional on this side of the spectrum, and it's extremal. It takes its maximum value when evaluated on the protected part. We have many advantages to carry on with this program in super young mills in the planar limit, because as I described, we know the spectrum, we know the exact spectrum. So when we are going to demand this positivity, we don't have to think of a continuum as we will usually do if we don't know what is above. We will just demand some continuum and demand that the function is positive in all this continuum. But because we know the exact positions of the spectrum, then we can demand positivity just at those exact positions. So then the functional could be a function that is positive at those points and even is allowed to become negative in between. So those are less constraints on the functional, and typically that result on better bounds when performing this optimization problem. So the spectrum is known, but that's the spectrum of the single traces, which is known. However, there is a caveat, because in this OP decomposition, the double traces still survive. So, and that poses some difficulty. So let me say some words about these double traces in the OP. So because we are considering the planar limit, we think of the 4-point function as being some series, right? It's stratified as the leading term at large n, and then the 1/n corrections. And in fact, the actual leading term just corresponds to the factorization of the 4-point function into two-point functions. This is known as the disconnected correlator. And already here, if we try to see what are the intermediate states, what we will find will be only these double twist operators or double traces given by these composites with some derivatives. And the OP coefficient of those double traces in this normalization I'm using, they are of order 1. Then we can go to the next correction in 1/n. That's what we really call the interacting part of the correlator. This is the planar connected correlator, and it appears at this subleading order. Here we have this connected, the 4-point function represented by this connected worksheet, and we now perform the cutting, and now is when the single traces appear for the first time. Now they come here with OP coefficient with this subleading with respect to this disconnected part. But we also have the double traces, because there will be 1/n corrections to this leading term. So they are appearing here. And because they are corrections, even the sign is not defined. So that poses a problem for our optimization problem, because that relies a lot on having some positive OP coefficients. Besides, also the position of the spectrum of these double traces is, so far we have not been able to determine by integrability, so that also poses some difficulty. If we were to do this problem at finite n, such a problem wouldn't exist, because we would start, there won't be this stratification, right? So we will start, by the way, with two positive coefficients, but because we're going to isolate the planar connected part, then we have this issue of having this subleading term with no sign, with no positive sign necessarily. So what I'm going to describe now is a way to circumvent that difficulty, to find a way to get rid of these double traces and still get some crossing equation or some sum rules that only depends on the spectrum of single traces, which we know pretty well, thanks to integrability. Now, the way I'm going to get rid of these double traces is by using what we call dispersion relations. This is just based on the fact that if you have some analytic function and complex plane, you should be able to reconstruct that function from the knowledge of its singularities and discontinuities. So the best known example is the case of the flat space amplitude that you can reconstruct from an integral over the imaginary part of the amplitude. And just like this result that is well known, there is a similar dispersion relation that you can write in conformal field theories. You can reconstruct the full correlator just from the knowledge of its double discontinuity, where here, just like the amplitude, actually the correlator also has a similar structure where these branch points correspond to the OPE limits. And this double discontinuity is a simpler object. Now, this should be integrated over some kernel that is something complicated, but has been worked out, so the formula is complete. And this is advantageous for us because now, when we are going to, if we plug in here the OPE decomposition of this 4-point function inside the double discontinuity, this will, after performing this integration, this will result in a new decomposition of the 4-point function. And this new decomposition will depend now on this double discontinuity of the conformal block, which will define for us what we call dispersive blocks or Polyakov-Regge blocks. And the advantage of those blocks with respect to the ordinary block is that they contain extra zeros. And these extra zeros are exactly at the position of these double traces or double twist operators. In fact, in more detail, if this is a non-protected operator, a non-protected double trace operator, this will be proportional to the square of its anomalous dimension, and that is further 1 over n suppressed. So in fact, because it becomes more subleading, we can remove it from the planar order. So now this results into a new decomposition of the correlator, which is a sum that is saturated only by single traces with their OP coefficients times now the dispersive block or Polyakov-Regge block, which replaces the ordinary block. So this is, from here we recover the full correlation function just from a sum over single traces. This is not yet crossing symmetric, so we can still demand crossing symmetry, and we define this function x to be this dispersive block in 2 different channels, and we get now an equation which is a sum over single traces, but in fact not only, even more restricted than just single traces, it only depends on non-protected operators, just on long multiplets. This is still not desirable because, as I described some slides ago, in order to carry our optimization problem, then the part that we need to extremize is the protected part that we know pretty well. And this sum doesn't contain it. This sum is not a sum that balances protected, low energy protected operators and high energy non-protected operators. It just is a sum rule that balances non-protected operators among themselves. So in order to carry on with our optimization problem, we need something more than this sum rule. And fortunately, there is a way to construct such sum rules. And this comes from this result of, which is known as integrated correlators. So an integrated correlator is defined as some integral over space-time or over all the cross-ratio space with some measure that makes this integral convergent. From here, you get rid of the space-time dependence, and you just produce a number that still depends on the coupling. Thanks to supersymmetric localization, in the market there exist 2 measures that we know, which we know what number we obtain thanks to a supersymmetric localization computation. So now we can plug in here our OP decomposition and obtain a sum rule, which will now be a sum over these OP coefficients times this function, which will be the integral over the dispersive blocks. And this will produce this number, which actually, thanks to localization, can be computed exactly. And in the planar limit is just given by this integral over Bessel function, so we can really have good control over any value of the coupling for this number. In fact, there are 2 of them, as I mentioned. So now we are equipped with 2 types of sum rules. Crossing sum rules, which balance non-protected operators among themselves to give 0, And these sum rules which actually contain both protected and unprotected operators adding up to this number that we know. So let me present a first attempt to perform this optimization problem with these two types of sum rules. The protected part of the crossing equation is 0 because the protected part is crossing symmetric by itself. And then we only have, in terms of the low energy part, we only have this part coming from the two integrated constraints. Here we isolate Konishi, and then we have all the other states above Konishi. So now we carry on with our program where we try to find a linear combination of these sum rules, such as these quantities completely positive for every state above Konishi, is normalized to 1 or -1 for Konishi, such as we isolate the OP coefficient, and is extremized on this part of the protected part, which in this case are just given by the integrated correlators. Here are the results for the bounds that we obtained. So let me start here with the orange part of the plot. In the orange part of the plot, we first pretend that we only know one integrated correlator. That is just like an exercise to see how this optimization problem works if we just knew one integrated correlator. And you see that here we get an upper bound, which is this orange curve. However, the fact that I am shading all the rest by orange, it means that there is no lower bound. We don't produce lower bound in this situation with one single integrated constraint. It means all this area is an allowed area for the OP coefficient. However, things improve if we now use two integrated constraints. In this case, the bounds that we obtain are these blue curves, the upper and lower bound. And as you can see, at the strong coupling, it's narrow. However, well, so we can say that already a strong coupling, this optimization problem is working pretty well. But then as we move to a smaller coupling, intermediate value of the coupling, and especially weak coupling, then the allowed area becomes pretty bad. So we have a big range that where the OP coefficient could lie. But we are not done yet. This is just an exercise with these tools, but there is an extra tool that I would like to introduce. I thought that the best way to introduce this new type of sum rules would be to go to mailing space. So here I am starting with the correlation function in position space and performing a mailing transform to define what we call the mailing correlator. And we can also write, just like I presented the dispersion relation, this double discontinuity on the position space, we can also write a dispersion relation for the mailing correlator. In fact, the way that dispersion relation works is very much alike like the well-known case of the amplitude. Here you start by some trivial contour, and then you deform it, you pick up all the poles. This poles corresponds to the OP states, the OP intermediate states. And then you have this arc at infinity that fortunately we can drop because the mailing correlator has a good behavior at high energy when this Mandelstam variable goes to infinity. In fact, it's such a good behavior that even if we now stick in a polynomial, depending on this variable of integration, the integral will still be convergent, and that would lead to a new type of dispersion relation. By demanding that these two dispersion relations, one without the blue factor and the other with the blue factor, demanding that they are identical, that they should reproduce the same mailing correlator, then that provides us, the difference between them provides us a new type of sum rules, which now also contain some protected part and some non-protected part. This is what we call as anti-subtracted dispersion relations. Now that we include this new family of anti-subtracting dispersion relations, we do a better job at finding bounds. Let me start again by the orange, which is the case where we pretend that we just know one integrated constraint. The upper bound is pretty much the same. However, now we do obtain a lower bound at the weak and intermediate coupling, although this is lost once we go to higher coupling. And the best bounds are still coming from the case where we know the two, where we input the two integrated correlators. In fact, the strong coupling part is pretty much the same as before, which means that in this optimization problem, the best bounds are still found from the integrated correlators and the crossing sum rules. However, now the region of intermediate coupling and weak coupling is much better. Now the gap that I showed before is closed, especially at weak coupling, and it becomes much narrow at intermediate value of the coupling. In fact, we can also compare this with our perturbative curve. So then you can see here the strong coupling and the weak coupling in green. Both of them pass through our bounds on the region of validity, And then on this crazy region, I mean, on the region where they become crazy, our bounds still provide some nice interpolation. Of course, the dream is to shrink these bounds such that we can eventually find the exact curve, maybe by including new type of sun rules. So, of course, a desperate question that we have is whether we can improve these bounds. And this may depend on the region of the coupling that you want to address, but let me address this question on this strong coupling region, the region of large G, where the CFT bootstrap problem becomes a simpler problem. As we know through holography, our 4-point function stress tensor should be dual to scattering of gravitons in ADS5. And especially when we take the strong coupling limit, if you follow this dictionary between the parameters on CFT and in ADS, the limit of large G corresponds to the limit of large radius of ADS. And in fact, what this means is that the amplitude in ADS now can be approximated by a flat space amplitude. And our CFT bootstrap problem reduces to a flat space matrix bootstrap problem, maybe similar to what we saw in the morning from Andrea. This problem is simpler than our CFT bootstrap problem, and we can use it as a toy model to address this question of whether the bounds can be improved. In fact, just to tell you a bit more about the dictionary, if you consider the low energy expansion of the amplitude, of the flat space amplitude, you get these low energy coefficients. And there is a map between these low energy coefficients and what we call integrated correlators. So the knowledge of our integrated correlators in this side of the flat space matrix bootstrap is the knowledge of is equivalent to the knowledge of these first two low energy coefficients. These problems become the same and the bounds approximate as G is large, but in fact not only the bounds coincide when G is very large. Also the extremal positive functional, the functional F, this linear combination of our sun rules, also that one coincides. Here the blue line would correspond to the flat space, the output of our optimization problem in flat space, which would be equivalent to G equal infinity. And this you can see is very well approximated by these purple dots that corresponds to the evaluation of our CFT functional. So the problems become really identical, provided that you take G to be large enough. Now, given that the problems match at every level, bounds and functionals and every detail that you can think of, we can play with, do some experiments on the flat space case. And something, well, as I described, the flat space amplitude we are talking about here is a 5-dimensional flat space amplitude. But we can easily play with the dimensionality, just, let's say, as an experiment. And in fact, what we find is that if we perform this optimization problem in flat space, but now in 10 dimensions, the bounds that we find on the coupling associated to this, in this case, would be a closed string and two gravitons, it becomes much tighter. The bounds are much better, in 10D than in 5D. So then you can ask the question of what does this experiment mean in terms of the CFT? So how do we recover the 10D flat space physics from the 4D CFT side? So the answer is just to consider not only the stress tensor, but also all the higher R-charge PPS operators, which are Kaluza-Klein modes of the graviton in S5. So this would be something that we hope we can address, and hopefully, and we have a hint from this exercise that will probably allow us to improve these bounds and get closer to the actual exact solution. So, okay, let me just summarize what we went through today in this presentation. So I introduced to you what we call dispersive sun rules, which are sun rules that are just saturated by single trace operators, which are operators that we know thanks to integrability. And in fact, there is a menu of this type of dispersive functionals. The simplest of them are just the crossing equation, but also I introduced these sun rules coming from these integrated correlators and also these anti-subtracted sun rules. The usefulness of them depends on the region of the coupling. As we saw, the strong coupling mainly, the job is done by the integrated correlators, and crossing is always there. You should never ignore crossing. But then a weak and an intermediate coupling, we also need the input of these anti-subtracted sun rules to get our best bounds. So we do get some two-sided bounds that interpolate all the way from weak to strong coupling. And as I described, there are some lessons from the strong coupling limit, where our CFT problem becomes S-matrix bootstrap problem. And we believe that from hints from this simpler limit, that if we consider mixed correlators that include Kaluza-Klein modes, then we would be able to improve these bounds. Also, here I just addressed the OP coefficient of Konishi, but in fact we can bound other observables. As long as these are observables that you can write as a sum rule of OP coefficients times this dispersive of Polyakov radio blocks, if you can do that for any observable, that will be something that we will be able to bound. So that includes the 4-point correlator itself and also other observables such as energy correlators. And of course, it'd be nice to see if we can perform this type of CFT bootstrap problem, dispersive CFT bootstrap problem, for other theories that are dual, that have open or closed string holographic duals, such as the theories that we will hear about tomorrow morning. Okay, thank you.
Thank you. Questions?
Hi. So you used this integrated correlators coming from BPS observable in deformed theory, right?
Yeah, so they are computed from this partition function of this mass deformed super young Mills.
So if you start from, say, 2-point function in, say, I don't know, beta deformed theory, but of two non-protected operators, but which become protected when beta is 0, and then differentiate twice to get some integrated correlators, and you can use a really non-trivial insight from integrability of beta deformed probably as well. Like as an
right. Of course, well, we will have to make sure that that is independent from this integrated correlator. I mean, if it gives something new or is just redundant, but if it gives something new.
Because if you start from non-BPS 2-point function, right?
Yeah.
And then, because your integrated correlators are kind of very BPS-y, right?
Ah, okay. Okay, I see what you mean. Yeah, so that is another way of improving our bounds. If we have more integrated correlators, that would certainly, I mean, as I was showing, one of the main points is that the integrated correlators do a very great job. There is a big difference even from considering 1 versus 2. So yeah, if you can do this, it would be great.
Other questions? If not, let's thank Frank again.
The microphone. Yeah.
So thank you for introducing everything. Should we turn it on?
Yeah. Maybe a quick mic.
Prova. Well, I guess. Can you hear me? Yeah. Yes. Okay. Oh.
So our next speaker is Alessandro Gergudis, who is going to tell us about hexagons and small spin to strong coupling.
Okay, well, first I would like to thank the organizers for inviting me. It's always nice to be in London, beautiful place. And I will talk about some recent work done with Benjamin Bassot, which is in the audience. And it is based on some a bit more ancient work done again with Benjamin and Artur, which is a PhD student at ENS. Anyway, let me start actually in the same way as Frank did, which is by saying how good is actually computing, that we can compute the spectrum in n = 4, and how this is one of the great success of integrability. What does it mean? Well, as Frank very nicely said and introduced for me, is the fact that using the quantum spectral curve, which is some mathematical tool that can give us a different, the value of the anomalous dimension for a single trace operators in the large n limit, in n = 4 at different values of the coupling. And this is a truly fantastic tool. I suggest you to go download the implementation by Dima and try to play with it for perturbative. It's very fun. And you can insert whatever you want, and this will spit you out practically the anomalous dimension for operators. This is, for example, the I think the 11-loop anomalous dimension for the Konishi. Of course, you can also go through finite coupling and compute the anomalous dimension, again, for the Konishi at different values of the coupling. You see interpolation from the weak to the very strong. I think this is some old, as there are way more nicer end result. And of course, you can also go to the strong regime in an analytic way. And this is some new result made by Simon and Kolya and Paul, where they actually were able to compute the Konishi anomalous dimension up to 1 over lambda to the 7/4 in the strong coupling. So this is fantastic. This is the spectrum. And as we heard, what can we do about the structure constant? Well, most of the results that we've seen are focused on computing the Konishi structure constant, which is super important, but one would like to push further. And of course, as we have seen, different methods exist, and there is no unified, at least we don't have a very good unified picture for all of this. So the result, as we've seen, it's practically the perturbative computation was done using Feynman integrals, and it's still stuck at 5 loops. Hopefully someone will try to push it higher. And we've seen from the talk of Frank that there is this bootstrapability framework that works extremely well, where we can have some interpolation between weak and strong coupling, where we get very good bounds. And this is some sort of a middle ground between the small. And of course, we can also study the strong coupling expansion as has been done through this analytical bootstrap or this ADS Virasoro-Shapiro amplitude, of which we'll hear about tomorrow by Shai and Maria. And we've seen that we can go through very small setup of anomalous dimension. We can go through all these stages, but we need to use different tools. So what can integrability give us that can interpolate between all these things? Well, there is something, which is this hexagon proposal that we heard from Benjamin in the first day, and from Frank briefly in the previous talk. And the hope is that this object, or some modification of this object, will give us something that we can actually use between these 3 different regimes in the same way that the QSC does for the anomalous dimension. Of course, this is a dream, as I will try to show that we have almost good control over the small spin, the small coupling, but finite coupling is still complicated. And the aim of this talk is to try and show you that actually we can do some things as strong coupling by learning some lessons from the anomalous dimension. Okay, very well. So let us start and jump into the single slide about the hexagons, and I hope it will be clear enough how they work. Very well. So I was a bit sketchy by saying what actually structure constant we care of. So in principle, we would like to care about structure constant of multiple spinning operators and things which are very nice and complicated. Unfortunately, they're too difficult. There are some results by Carlos, Pedro, and other people where they try to compute the spinning 3-point function from OPE of higher point function and hexagons. Very nice, but unfortunately, it's very difficult to push this forward. So we will focus on a very particular setup, which is practically a very reduced sector. So n equal 4 in the planar limit has a huge symmetry, and we will only focus on what is known as the SL2 sector, which is somehow like a simpler subsector of the whole theory, where we only care about operators which are built up by light-count derivatives and some complexified scalar combination. So the numbers that appear here will be important, so let me focus on them. So the spin of the operator is identified by the power of the derivative, and then the length of this operator is connected to this twist of the operator. And we have, of course, I would like to do spinning. I can't, so I need to reduce to actually try and do this protected half BPS operator. So this will be my playground for today. So I'm only caring about this sort of structure constant. It would be nice to extend, but it's very difficult. OK, let me present what is this hexagon proposal for computing structure constant. Can be pictorially represented in this way. So the idea is practically you take a 3-point function represented in this way. We have the non-protected operator on the top, and then we have the 2 protected operator at the bottom. And the idea is that I can cut through these different seams, and I can construct a more fundamental object that, as we've seen from the talk of Benjamin, can actually be used also for constructing higher point function through what is known as hexagonalization. So this building block I can bootstrap using integrability, and it has some form which, will be important, and we'll present it later. But for now, I just wanted to understand how, reconstructing the full structure constant works. So I can build up these 2 objects, think of them as some sort of form factor amplitude, and then I need to glue them back together to reconstruct the starting the starting 3-point function. So by gluing back, I really mean inserting some sort of infinite sum of state between all the seams, and then performing the integration over the rapidity of the particles that I've inserted through the seam, summing over all the possible bound state that I can insert, all these sort of complicated things that are represented here by this scary-looking integral sum sign. Okay, all of this can be done, and of course, all these sums will act to some loop order depending on how much length this operator have, and I will refer to these different quantities LA and LB as the two bridge lengths. So this is, let me call it the adjacent bridge length, and this is the bottom bridge length. So depending on how big my operator is here, this I will have way more connection here, means that actually this particle will have to interact with more of the physical state, meaning that this will be pushed. Or in a different way, this exponential will become more and more dumped the higher these lengths are. Okay, very well. This is like some sort of schematic idea. And importantly, we see that actually the different contribution that come from this gluing back these three different seams actually factorize in the hexagon proposal. Okay, very well. So schematically, what I really would like to do is practically what I was trying to explain before. I want to take these two things, glue them back. And the first thing that I can do perturbatively is, okay, let me take 3 vacuum state, I can insert them, and I can glue this, and I have I can construct some structure constant to some loop order. If I want to start adding, go higher and higher in the loop order, I will have to, at some point, start inserting particles in one of the edges, and the first one to contribute is the one in the bottom bridge. Okay, so I start inserting a particle in this bottom bridge, and I keep on doing this over and over again. And this, in some sort of sense, is how I can construct perturbatively structure constant starting from the hexagon. Very well, I arrive at some point where, unfortunately, some effects come into play, which are called like wrapping effects. You can think of them as some sort of finite size effect. The fact that actually my operator has a finite length is not infinite, so at some point I can have mirror particles here generated, interact with themselves, and then being reabsorbed. So what we did with Benjamin and Artur was actually try to account for all this possible wrapping contribution. This is one of the possible contributions to the bottom bridge. There is another one which actually interpolates between the 3-1, and it was very important to construct this conjecture for how this finite length hexagon should work. And so what we found is that actually there is a natural way of implementing some building blocks from the QSC, which are these transfer matrices. You can think of them as appearing because, okay, you can imagine that I can insert one particle here, then it needs to interact with all the physical state, and how does interaction with physical states, is encoded in an integral system, usually through transfer matrices. So this is some naive idea that one can have and how this works. And the point is that, okay, I have 2 different sort of setup of transfer matrices that I can build up. One comes from this adjacent sort of bridge, which are encoded into some, okay, for the expert in the room, SU2/2 non-compact representation. And then this bottom bridge is encoded into this transfer matrix, which actually is SU4/4 compact representation. So what I try to explain with this slide is that, okay, we have some control on how to compute structure constant, mostly Edwick coupling through this expansion that I tried to explain. We have control over this finite size effect. We have something that allow us, in principle, to compute structure constant Edwick coupling. Okay, very well. But what happens if I want to do things in other regimes? So if I want to go other regimes, as you can imagine, strong coupling is still super complicated because I have to account for more and more of this integral, more and more of this particle, which means that I have to account for more and more of these integrals, more and more of these sums. This becomes a very complicated object really, really fast. So we need to actually think a bit outside the box, or at least learn from what has been done before, for example, the anomalous dimension, to try and figure out how can we overcome this complication and try to use the hexagon to compute things at strong coupling. So of course there is a caveat to what I said. You can actually go to the classical string regime where your operator and the spin of your operator is really large, and in their regime you can actually use again integrability of the worksheet, and this also allows you to study this if you want seemingly easier strong coupling regime. So what can we do? Well, for the anomalous dimension, I think 11 years ago, 12 years ago, was found that actually if you go, for example, to strong coupling, you can assume that there is a regular expansion of your dimension of your operator, and actually it's a regular expansion. What does it mean, a regular expansion? It means there is a polynomial in S. And if I, for example, try and study how I can solve the problem of the anomalous dimension at small spin, I can see that, for example, I can fix the first order of my expansion at strong coupling by doing a small spin expansion. Okay, this is fantastic. Can we think of doing something similar for the structure constant? Well, we can try, and since, as I mentioned before, we have constructed an ansatz for the structure constant in terms of QSC building blocks, that means that actually we can use all the results that have been found for expanding the anomalous dimension at small spin to actually try and construct things in the structure constant. Again, it's a bit weird to try and do it. It's weird also to try and do it here, but since you have the QSC as a construction, you can do it mathematically in this sense, but it's important. It would be interesting to understand actually what happens to your local operator when you expand it at small spin in some sort of way. Here I'm representing the leading radial trajectory where all my SL2 operators are. So for each, I have one dot at each value of the spin, and they go to infinity. And you see that what I want to do is that I want to expand close to this BPS point. So I want to expand close to S being equal to 0. And OK, I can do it, as I said, in a more mathematical sense, but I don't have a clear field theory interpretation of what does it mean to actually go to this small spin limit. But OK, nevertheless, as I said, I can take the small spin limit for the QSC. So I can think of it as some sort of like a solution. So imagine it that somebody gives you these P functions that come from solving some complicated, well, not so complicated, some QQ relations. And the solution has been found again by Collia and the collaborator up to the second order in spin, which is known as the curvature. And for us, it will only be important, we'll only care about the leading order in S, which is called the slope. And so the idea is that, OK, I have all these functions that are given to me by the solution of the QSC. And now I just want to point your attention to the fact that all of these are actually coupling dependent, which means that I have actually control in the small spin limit on actually the expansion through weak and strong coupling. The x here are actually your Zhukovsky variables, which is a canonical way to represent the rapidity or the kinematical value for your state. And OK, epsilon in this case is actually a function of the spin, and we see that all of these scale as something which is square root of spin. And J in here is the length of the operator that I want to study. Again, for the expert in the room, actually at this order, the P and the Q are actually proportional to each other because the QAI matrix is actually diagonal. It's diagonal and an identity. OK, very well. What does it mean? Well, as I tried to explain before, in this hexagon formalism, we have more or less 3 building blocks. One is the normalization, which encode the information about the state. I've not talked much about it because actually this is a very complicated object, and people usually try to avoid it. This is written in terms of Fredholm determinant. And as we will see, it will be complicated to try and extend it at small spin, but I will say more about it later. And then we have these 2 bridge contribution. As I said before, there is the bottom bridge, which is the one that I presented as an example of how to construct perturbatively the hexagon. And the other one is the adjacent bridge, which is when I insert mirror particles in one of the 2 adjacent seams. OK. For the sake of simplicity, let me just focus on the bottom bridge. And let me try and understand what happens when I try and plug in this small spin expansion. Well, we have seen from our QSC construction that we can write the contribution from one mirror particle insertion in this way, depending on this transfer matrix. This transfer matrix is constructed by a product of Q function, but they're actually the same, they're the same as the P function. So I can take this function, multiply by themselves, sum over the index, and I need to analytically continue one of them to actually construct this transfer matrix, which practically means sending x to 1 over x. OK, very well. I can do this. I can plug it in, and then I can start seeing what happens. Well, the first thing is that actually, if I want to construct only the leading order in S, I don't have to account for multiple mirror insertion, because all of these are suppressed in higher powers in S. How do I see this? Well, we see that this P scales as square root of S. This is a bilinear object in NS, means that this will scale as S. And OK, how do higher mirror particle insertion look? Well, they will look as product of this integral intertwined with some kernel that will link the 2 mirror integrations, which means that they will be quadrilinear, sextilinear, and no higher order in this P function, which means that it will be suppressed in higher in the small spin limit. So this is one of the first simplification of this small spin, is the fact that actually I only need to account for a single mirror insertion. I don't need to account for multiple mirror insertion. This is a very good news for us, because then we only need to do one integral. And as I mentioned, we have full control over the coupling. So in principle, we're very good. Now the thing is that, of course, you can start asking, OK, what happens about A and N in the small spin limit? Well, A follows from B. You need to do some contour manipulation, which are a bit too technical, but the idea is that there is some relation between the transfer matrices in the SU. The transfer matrices that build up the adjacent build in the QSC and the one build in the bottom, and you can prove that the one appearing practically are the same as small spin. This is some property that is not valid at finite spin, and actually is valid only for the physical sheet at finite spin. But anyway, at small spin, I can relate the two transfer matrices, which means that I can rebuild the adjacent in the same way with the same very simple transfer matrices of the bottom one, up to a fact that I need to analytically continue the length of the bridge. So now the length which appear in here will be actually, I will need to insert it in with a negative value. So if I study some integral for some length of this bridge B, which means some combination of the length of my operator, if I want to study the same, for the adjacent, I need to insert minus the length of the adjacent bridge. Okay. As I said, what about the normalization? Well, unfortunately, the normalization cannot be, we don't know how to expand it at small spin because it's as I said, it's a determinant, and the determinant depends, the dimension of the determinant depends on the spin of my solution, which I'm trying to compute the normalization of. This means that if I try to analytically continue a small spin, I need to compute the determinant of an object, which is actually a zero-dimensional one. We don't really know how to do it. So unfortunately, up to now, it seems like we're only able to compute the ratio of two different structure constants. So we need to compute objects, if you want to extract information at small spin, that doesn't have dependence on this n. OK, very well. So what can we do with this integral that we want to study? Well, we can start analyzing it, and we can see that it has a very nice properties. First, let me just do some change of variables. So I have defined x and y that appear in the transfer matrix as some, these are the shifted Zhukovsky variables. The index plus a means that I'm shifting plus ai over 2. Minus a seems that I'm shifting u, but minus ai over 2. So I can look at the transfer matrix, and I see that as again, a dependent on the two shifted Zhukovsky variables, and also on this ratio of Bessel function, which is something that happens. These are sometimes can be also rewritten as Koch sinh functions. I should stress, and I was a bit skipping over it, this is the solution for even j. There is also an analogous solution for odd j, but the two, once I will arrive to my results, the two will actually, our result will extend to all values of j. Okay, very good. So let us look at this integral. Well, first of all, there is this very nice kernel that to people who have done some localization reminds them a bit of localization computation. Where did this came from? Well, at some point where we did this change of variable, we were able to extract all the dependence on this shift A, and in my definition, there is a sum of array, and this sum of array gives me this kernel, which for the people who have done the curvature computation is practically the same as the curvature kernel once you've done some partial derivative. So in some sort of sense, what we see is that computing the structure constant seems to be similar, or at least computing these pieces of the structure constant seem to be similar to computing pieces of the curvature. They have a very similar structure, and the type of integrals that appear are very similar. There is also some other caveats that I should explain, is the fact that actually for the people who know how this t behaves at large values of u, know that it is actually exponentially enhanced. And so you will say, OK, this integral, you cannot compute it. Does that make any sense? Well, you need to add a prescription. This is also true for the hexagon when you compute them at finite spin. And the prescription that we found that would work to match perturbation theory or computation done from perturbation theory is actually to take some particular cut of the transfer matrix that actually practically drops out this exponential piece. OK. The last thing that I would like to add is the fact that actually if you try and compute this with A, you see that this A, given the fact that I've put a negative bridge, actually gives you some logarithmic divergences when computing them. So you need to regularize them, and there is some redefinition of this exponential that we can use to actually regularize them and extract the correct result. Very well, so now we are actually equipped to study our weak coupling small spin and see what we can do. Well, actually, we can actually solve this integral for whatever value of j and l that we want. And actually, this is written as an infinite sum of some gamma function and single zeta values. OK, very well. That's very nice. What we did to actually do this, well, we implemented some hidden symmetry that you don't see, but it's very clear from the hexagon picture. The fact that actually the left and the right bridge actually are the same in the sense that they can be intertwined by some change of variable. Very good. Okay. Well, now we can play. So we can actually plug it into Mathematica, expand it for once to how many loop orders we want. I think this is 14, just for the sake of it. And of all of this, this is the result for j equal 2 and LB equal 1. And it's the only one that actually I can test against perturbative computation, because I cannot construct a spin, a function in spin for higher twist. I don't know what is the basis of function, but in this case I know that are harmonic sums, and so I can then take the small spin limit of these harmonic sums, and I can test that these first two orders are actually compatible with with perturbative computation. Very well. Okay. So far we've done perturbative computation. Very nice. But what can we do with strong coupling? This is what we want to do. And so what can we extract from our result? Well, we now want to study this f of j at strong coupling, and we see that it is useful actually to rewrite it in a way that we've seen from Bercel talk on Monday, which is in terms of something that really looks like a Tracy-Widom distribution, and maybe this is the case. And also, for people in the audience who have done some integrated Wilson loop computation, the structure of this f of j is very similar to the one of the matrix model coming out of this computation, which may hint at the fact that indeed, when you try and do this small spin limit, you need to use non-local operators to actually express the form of this small spin expansion. Anyway, so okay, this is something that we can study. And actually, what we can do, we can plug it into Mathematica and try to actually expand at leading order in G and try to resum in this N. It's very important to notice that we have an infinite sum in N, and this is actually very bad for us, because after the first order in G, we are actually unable to resum. The two things do not commute, and so if we try and do the first G expansion and then sum in N, this doesn't work. The thing is, you get that higher order will contribute, and they are enhanced. So what we need to do, in principle, will be to resum over N and then do the large G expansion. We're not able to do it, so we actually have to go and use numerics. So how do the numerics work? Well, let me just simply say you're plugging in some values of G. In this case, it's easier to work with G and not with lambda, that we will use later on. And G is, again, the top coupling, and lambda is the top coupling. And at some point, you want to plug in different values of G, interpolate with basis of function that you guess from the analytic expansion, and then, of course, some basis of variables. And as I mentioned, you can do this. You can plug it in. We have a full solution. We know everything. And you do it for different values of L to some precision of 20, 30 digits, and then you try and reconstruct what are the values of this coefficient. Okay, for example, these are some results for j equal 2 and different values of the B bridge. Okay, but we see that actually there is an overall structure into this result, which is the fact that actually we can see that there is a bit which depends on the anomalous dimension expanded as small spin, plus some polygamma functions and some logarithmic depending on lambda. And there is a bit which is almost polynomial. There is a pole in 1 over j in the adjacent bridge, but this is expected from the fact that the adjacent doesn't have a nice limit for j going to 0. And we know that this thing depends on, this is only depending on the j, l, and the zeta values. Okay, very well. What does this tell us? Well, since these are psi function, we know that they might come from some expansion of gamma function. So what we can do is that we can cook up, based also some previous result by Benjamin and Deliang, some, let me say, finite spin representation for the bottom and the adjacent bridge in terms of the quantities that appear. So in this sense, this is a strong coupling expansion that we believe should be valid also at finite spin. Of course, we cannot prove it, but it's a natural extension based on results coming from this BMN limit studied in the literature. And if we take this and expand it at small spin, we see that actually we can, of course, reconstruct the results from before. And the important bit is actually to notice that we have to practically, there are these two pieces, dB and dA, that seems to admit some nice expansion in the spin. Again, in this case, of course, I'm still doing small spin, so this dB, I only know up to leading order in spin, but I know that this is polynomial bit in terms of j. So there seems that I've managed to encapsulate all the difficult contribution that come, then these non-analytical bits into these prefactors, and have managed to find some sort of nicer object that I can study. Okay, very well. So far, what have I done? I've tried to construct the small spin expansion for the hexagons. I have seen that I can study this at weak and strong coupling, and at strong coupling, I found this very nice form. Okay, this is very tantalizing, and you think like, okay, maybe I can actually make some bold conjecture. As we heard from Benjamin, conjectures are for free. So I can think of, okay, maybe this nice structure, actually, it's also there for the norm. And I can think of some sort of way of encapsulating all the complicated bit of my structure constants, all these non-analytic dependence on the quantum numbers, in some prefactor that I can think of it in two different bits, one that depends only on the R charges and one that depends on the ADS quantum numbers, which are the dimension and the spin of the operator. And these two encapsulate all the complicated analytical part, non-analytical behavior in spin of the structure constant. And then I'm left with this reduced structure constant D, which depends on the different charges of my operators, and also the spin S. But as we've seen, we know that, okay, from normalization, we can see that D has to go to 1 at leading order. But we know that we can make some sort of assumption following what has been done for the anomalous dimension that maybe this log of D, as we have seen from the small spin, may admit a regular expansion on small spin. What do I mean by regular expansion? I mean that this is actually fully a polynomial in S. And each term of this S expansion is itself, a coupling-dependent quantity. But all of this actually is very nice, because at this point, I can, of course, continue expanding at small spin and higher order to fix this coefficient. But I can also study different regimes of my structure constant. And this DJ naturally interpolates between these different regimes, because it's a very nice analytical form. And I think similar object was also presented in Frank's talk, is that we had to renormalize differently, because we really want that our D is, as a very nice irregular expansion. This is fundamental for us, because otherwise we're not able to fix this D by studying different limits. Okay, very well. So we have this conjecture, which is, based on our results at small spin and also some other results in the literature. Okay, and now the game, what it is? Well, we want to see how much we can fix of this D. So there is another, ace on our hand, which is actually trying to study this classical string regime. And what does the classical string regime give you? Practically, it allows you to fix all the terms in this D expansion of this Sn plus 1 square root of lambda of n. And we can do this for several orders. And what does this classical string practically thing is the fact that at this point, I'm solving like a minimal surface area problem in ADS. And what are the extremal of this thing? Well, there is 2-point-like strings that represent my BPS operator, and then there's this classical string, which is practically my states once I take the coupling and the spin to go to infinity, leaving the coupling and the spin to be fixed. Of course, I want to expand this in some other regime, which is when I take this redefined quantities to be small. I can do this because my D is a very nice function. And I want to add that actually as we will see, the pole in 1 over j, okay, it's not shown in the classical string. It's subleading, but we will see that actually it cancels with some computation in the norm. And I want to add that the norm actually we can study in this classical string regime in the small spin expansion without in the short string regime, which means that actually we can check that our conjecture is valid. Okay, very well. So now we have everything, and let's just see what we can do with all the tools that we have. Well, we can fix actually D up to 2 loop, which is, I think, up so far, if I'm not mistaken, the state of the art. And we can do this by using a mix of our classical and small spin expansion. Once again, I'm doing this for these leading edge operators, where now, of course, I'm beyond the small spin limit. So this is a finite spin result. I want to stress on this. We have used the small spin, which is these purple ones, and the classical limit to fix this coefficient. But this result is valid for whatever value of S you plug in. And this J vector is practically a combination of J1 plus J2, which are the R charges of these two operators. Very well. OK, there is a caveat, as we see in my fix. The fact that actually we cannot fix this S2 because it's beyond our capabilities with this 2 regime, but we could fix it by checking a comparison with the 2-2-2 result. And we know from the classical limit that there cannot be no J dependence in this coefficient, because otherwise we will see it in the semi-classical, in the classical string regime. I also want to point out that this first correction is actually universal, meaning that this object is valid, it's independent on all their charges, which means that once I factor out all the gamma functions, I am left with something that is completely independent and is valid for all possible operators. Very well, so this goes me to my conclusion. So I hopefully presented some by now extensively tested conjecture for computing the structure constant using this hexagon formalism, also in the short operator, for short operators. I have somehow show you that actually we can probe using the fact that we have a QSC-based formalism or the regime, like for example this small spin regime, and actually by merging this small spin regime with the classical limit, we're able actually to probe the structure constant at strong coupling, which it's very nice and good. So then let me leave you with some outlook. Okay, the idea is that can we maybe push this to other regimes, large spins, subleading trajectories? I don't know. It would be interesting to connect this to some SOV-like representation, as we will see from Carlos on Friday. And what happens? Can we do beyond leading end? There were a lot of approximation that I had to do to actually be able to compute the different adjacent bridges in small spin. Will this work at higher order in spin? Can actually we derive some small spin representation for this end? Can we finally be able to do the norm also at small spin? So fix this Fredholm determinant to small spin limit. And also it's very interesting and a bit outside of integrability, but it was very nice maybe to understand if actually the operators what happens to the operator in the small spin limit, and if actually one can think of them from some light array operator. Before finishing, I would like to say that this is 20 years of IGST, and so I was very taken and wrote some nice poem about it. Well, not exactly wrote myself. I used ChatGPT, but you can actually ask it to do many things for which spell IGST in the first line. Anyway, with this I finish. Thank you.
This is the question in the back of the room.
Sorry, I cannot hear you. Can you speak a bit loud there? Yes. Yeah. Yes, exactly. So this is done through Fernando. So what we did, we took our reduced structure constant, we applied it to Fernando result, and we checked that all this number match with our result, and we saw that, and we could extract this. So the two actually match with between the two different approaches.
There's another question by Julius.
Can you comment more on extending to subleading trajectories so you don't have a near BPS expansion? Is that?
Yeah, that would be complicated. I don't know if this. Yeah. Yeah. Sorry. What did you say? There are no BPS operators on the subleading. What did you? Yeah. So it would be difficult. I think it would be as complicated as trying to expand close to one of these points, which are, yeah. The nice thing about this is that you're expanding something which is some sort of vacuum. So.
But then we can use Andrea and friends trick, no? Take the subleading, do Reggie bridges, and make it go to the leading trajectory.
I should add that whatever you want to do, it may interfere greatly with the fact that you can do this integral. This integral can be done in this regime because we know the prescription for doing it, because we could also match it with perturbation theory and guess what was the correct prescription. But we don't know in general how to do this. Even a large spin, it could be that we cannot actually perform the integration. There is some problem. You know that this T function scale as u to the s. So, okay, yeah. For small s, makes sense that you can do it, but for large s, okay, who knows if you can actually do. Yeah.
Claudia?
Very nice. So could I ask, so I understood that you use pieces of QC to some wrapping corrections, right?
Yeah.
In the hexagon format. But at the same time, I think leading S term for the spectrum is actually doesn't contain wrapping in n equals forward. And in ABJM it does contain. So to which extent you actually probe your construction with Benjamin, or you can use just bare hexagons without?
So, so there is, I should cross-check this. This is what I remember, but if I do remember at some point, there is some bit that you can think of it being if you want. It's not exactly true. So it's true that in the large S, you're only probing this ABA sort of regime, like this easier bit. But there's still wrapping inside on this. It's wrapping, I think, in a different sense. You're like, you have this single mirror excitation, but of course you have all the possible renormalization of the operator on the outside. I mean, I think there is some bits, but Benjamin can maybe contradict me. I think at 5 loops, if I remember correctly, you would see that there is a bit which only starts at 5 loop, which is where you expect the first, this effect to come into play. So even when you construct this object, which is the transfer matrix, you see that there is a bit which is, okay, start from 2 loop and goes whatever you want. And there is another bit which seems to be only 5 loop and over. So you can think of it as some sort of, in the same way as you see the wrapping in the canonical hexagon. But I don't have any more intuition about this, I would say. Yeah. 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 That's true. So there is this secondary wrapping that you need to account for, which is suppressed, usually at decoupling, come into play at 5 loops. And you need it to actually construct this compact T transfer matrices, which means that if you want to do it with a compact T, you would miss half of the answer up to 5 loops. So it would work only to so. So that one probably doesn't account, but this is another type of wrapping that you need to account for. So there are 2 different. Yeah, that one will be at higher order, and you would need to care for it. But indeed, sorry, there is this secondary wrapping, which is like this subleading wave that you have. Sure, yeah.
Okay, last question.
Can you show the slide with the huge data? Yes. So how do you get this? It's like writing this structure constants like this harmonic sums, and then just an S0 or something.
Oh yeah. So you need to do something very annoying, which is do a lot of spin, interpolate with the basis of harmonic sums, and then take the limit of the harmonic sums for S that goes to 0.
Yeah, about that, I think on this work of Pedro and Alexandre, when they were trying to do that for twist 3 at least, which I think this is twist 2, right? This data or no?
Yeah.
But when they were trying to do that for twist 3, this naive analytic continuation, let's say, was not the ones that they were finding when they were trying to analytic continue in spin. So, but it works for twist 2, but I don't know.
Okay, I mean, I would not even know what is the basis of function to use for twist 3. I mean, some of them you can, but...
they were doing some one-loop stuff there.
Okay, okay, interesting.
Okay, so let's thank Alessandro again. And we'll have a 45 minutes break.
Hello? Working fine? Okay.
Working fine, right?
Yes, I think so.
Okay, then we're all set.
All right.
Yeah, maybe we should wait.
Yeah.
Did somebody announce that it's the end of the break? I didn't, but I don't know who's supposed to do it. I don't know who's responsible with something. It was not in my...
There is another mic.
No?
Yeah, maybe I can see. Right, just before we start the talk of Shota, just to remind you that the poster sessions, which is now being prepared, is after this talk. And those who survive till the end will be allowed to go to the 8th floor and have a reception, which will include some food and, most importantly, drinks. Thank you.
Okay, so I think we can start with the last talk of the afternoon by Shota Komatsu about Coulomb branch and the integrability.
All right, so thank you for the introduction, and also thank you for the organizers for putting together this wonderful work conference. So yes, today I'm going to talk about our recent work together with Frank Coronado and Costa Zarambo about Coulomb branch of n equals 4 supermills and integrability. And let me also mention that when we started this project, we were also discussing a lot with Clay Cordova, so like a special thanks to Clay as well. Well, Clay, yeah, I didn't put his name here, but okay. All right, so let's start with some motivation and introduction. So this is the 21st edition of IGST. So finally, IGST became old enough to drink alcohol. So, well, in the US. So we have seen impressive progress over the past years about n equals 4 supermills, planar n equals 4 supermills. For example, like exact computation of the spectrum, and then non-perturbative results of amplitudes, correlation function, and also various kinds of defects. But I think it's worth reminding ourselves why we were so excited when we first found that n equals 4 supermills might be integrable theory. So one of the reasons why it was so exciting was because there was some precursor to all these developments, which was actually found in the actual QCD, especially in the high energy limit. And in particular, it was found in the so-called BFK limit, and it was formulated by Fadeev and Korchemsky as a kind of integrable spin chain, describing this high energy perturbative regime of QCD. And also, I should also mention that this idea of using integrability to study Yang-Mills theory, like actual Yang-Mills theory or QCD, is also something Feynman really wanted to do just before he passed away. So which you can see from this Feynman's last blackboard, and you can see this beta ansatz. And also you see that he writes he wants to know how to solve theory, or Well, anyway, yeah, I'm not sure if I can read. Okay, so yeah, so then it's worth asking this question again, probably. Can we use integrability to learn something about QCD or YAM mills? And well, we have seen already a nice results, especially in this BFK limit of n equals 4 super mills, thanks to many people in the audience. So the point is that the BFK limit of n equals 4 super mills captures the most complicated part of the BFK limit of YAM mill theory. And you can actually derive and systematically extend the BFK result, which was obtained before, using sophisticated techniques like a quantum spectral curve. And also there is another completely different appearance of integrability recently in the context of QCD flux tube, found by these people. And we will hear something related from Barak tomorrow, I guess. And in addition, if you go down to 2D QCD, there is some emergent interesting structure found by these people. So what they found is that you can actually write down a Q system or Q functions which govern the meson spectrum in 2D QCD. And so today's talk is to propose yet another way of making n equals 4 super mills a little bit closer to the actual YAM mill theory or QCD, which is to study the Coulomb branch of n equals 4 super mills. So the Coulomb branch of n equals 4 super mills has an advantage, is that studying them allows us to break conformal invariance while actually maintaining the full quantum integrability that we already found in planar n equals 4 super mills. And furthermore, going to the Coulomb branch allows you to introduce the mass scale to otherwise conformal theory. And having a mass scale allows you to study various kinds of new observables. For example, the vacuum condensate, which is basically a one-point function of local operators, or something like a meson spectrum. Precisely, it's actually W boson bound state. And also scattering amplitudes of mesons. And we'll hear something related from Elisabetta tomorrow or maybe day after tomorrow. Okay, so that's kind of why studying Coulomb branch of n equals 4 super mills may be interesting. And of course, just studying each of them doesn't allow you to really study YAM mill theory, but the hope is that by studying all these aspects or all these different regimes, maybe you can learn some lessons that apply also to actual YAM mill theory or QCD. Well, at the end of my talk, I will also mention yet another possibly more interesting setup, especially well, I will mention that in the last slide. Okay, so let me just explain more clearly what's the setup of Coulomb branch of n equals 4 super mills. So Coulomb branch basically means that giving a kind of web to one of the scalars in n equals 4 super mills, and then go to some regime in which gauge symmetry is spontaneously broken. And there are different ways of doing it, but the one that I'm going to talk about today is the one in which UN gauge symmetry gets broken down to U1 times UN minus 1. So this can be achieved by turning on this kind of web in one of the scalar. So you just turn on one component. Okay? So from the D-brane picture, that means that you have n D-brane, and you just separate one of them. And the distance between n minus 1 brane and this probe 1 brane is given by this number v. Okay? And you can also kind of consider the holography for this setup. And what holography means in this setup is that you basically replace this stack of n minus 1 brane by some ADS geometry. And if you do so, you are left with this a probe brane. So now you have some ADS 5 times S5 spacetime with a probe D brane. And then probe D brane sits at the z coordinate, which is inversely proportional to the expectation value. Okay? And in this setup, perhaps one of the simplest observable in this context is one-point function of local operator. So of course, a one-point function vanishes if you preserve conformal symmetry. But now, because you broke the conformal symmetry by introducing a vacuum expectation value, so now you can study the one-point function. And especially, let's consider the one-point function of a single trace operator. And so that is holographically given by some a closed string emitted from the boundary. So that's where the operator is inserted. And then this closed string worldsheet gets absorbed by this probe D3 brane. Okay, so this is a space-time picture of this one-point function in holography. And from the worldsheet point of view, this is just nothing but the overlap between the closed string on-shell state and the boundary state corresponding to this probe D3 brane. Okay? And the punchline of my talk is that this boundary state is actually what's called integrable boundary state, which has a very nice property, and you can actually determine this boundary state explicitly at finite to foot coupling using integrability. And using the structure of the boundary state that you determined, you can even kind of write down some finite coupling answer for this one-point function, which takes this kind of like a horrendous form. And I'm going to explain each of the ingredients in the rest of my talk, okay? So this the important part is like these three parts, and this determinant is what's called it's some super determinant of what's called Gordon matrix. But this Gordon matrix is some matrix whose element is a logarithmic derivative of the beta equation. So once you know the beta equation, you can write it down. And whereas like this part, which is a complicated function, which depends on the rapidity of the particle, is coming from the reflection matrix that describes the boundary state. And finally, there is some interesting kinematical factor. So let me explain these three elements one by one, and that basically fills the rest of my talk. So let's start with the superdeterminant of the Gordon matrix, okay? So to see the emergence of the superdeterminant, or why it's important, you can actually see it already in the weak coupling. And precisely speaking, you can actually see it already at the tree-level computation. So how do you compute one-point function of local operator or vacuum condensate at tree level of n equals 4 supermills? Well, that's very easy. You just write down the operator and replace the operator with its expectation value, which is just given by this. So this is a kind of like a simple field theory analysis, but you can also rewrite it in terms of the spin chain language, because we already know the map between the single trace operator and the spin chain, thanks to the works by many people. And for example, if you consider operator made out of just scalar, like a 6 scalars, which we call SO6 sector, and this can be expressed as a spin chain overlap. So this B is a particular boundary state whose vector is basically given by the a direction of the vector of the vacuum expectation value. So this is a kind of like a trivial rewriting of the field theory computation into the spin chain language. But what's surprising is that this boundary state is known to be what's called integrable boundary state, and in particular, it is annihilated by infinitely many higher spin conserved charges that exist in the integrable spin chain. And using that property, people already actually derived analytically that you can actually compute this object overlap in terms of this kind of like a formula. And in this here, you can see the superdeterminant. So the details of the formula is not that important. It's for those who know the subject, it's obvious. It's just like a logarithmic derivative of the beta equation. For those of you who don't know, I don't have time to explain. So, but you can at least have a feeling of what it is. And so this is a kind of like tree-level answer. And so now, of course, this is just a tree-level answer. And the nice thing about this part, the superdeterminant part, is that we also know the finite coupling generalization of this Gordon superdeterminant. Because we know the beta equation at finite coupling, thanks to Nicholas, Matthias, and other people in the audience. But what's not obvious is how to generalize other parts, especially this part, which is given by what's called Q function, which depends on some rapidity of the operator. Okay? So that's the next thing we need to figure out, okay? So that brings us to this next part, all right? So, and the punchline here is that this complicated part is actually coming from the structure of the boundary state, okay? By the way, how much time do we have? 20 more minutes, okay. All right, so let's talk about the next part now. So so as I said, like I mentioned that like this part is related to the structure of the boundary state, or more precisely, what's called a reflection matrix. To see that, like let's consider like overlap between the boundary state and then two particle state. One magnum with momentum u and the other magnum with momentum u bar. So here u bar is actually minus u. So pictorially, like this overlap, you can think of it as a process in which like a two magnum states gets absorbed by this boundary state here. Okay. So this at this point doesn't look like a reflection matrix, but if you rotate this picture by 90 degrees, then you can see that this is actually nothing but the reflection process in which like a magnum with momentum u gets reflected by the boundary, and you get magnum with momentum minus u. And so, of course, like this rotation, well, you can understand it pictorially, but if you want to be more rigorous, you can do it by what's called mirror transformation. And the key point here is that this reflection matrix, you can actually bootstrap at finite coupling by imposing various consistency conditions, which I'm now going to review. Okay? So what's the first consistency condition? So the first consistency condition is the symmetry requirement. So if you consider some symmetry generator G, which is preserved by this Coulomb branch configuration, then this boundary state needs to give 0. So the boundary state needs to be annihilated by the symmetry preserved by the Coulomb branch. And this symmetry generator in this case, is basically like a supersymmetry generator inside a PSU2/2 square, which Nicholas talked about yesterday. Because like the Coulomb branch of n equals 4 supermills preserve all supersymmetry, but breaks all superconformal symmetry. So you just like pick the supersymmetry part of the PSU2/2 square and require that this boundary state is annihilated by this symmetry. And so this is a kind of straightforward exercise. Because we know how the symmetry generator acts on Magnon, again, thanks to Nicholas and other people. And if you do this analysis, you discover that actually this two-particle overlap is almost uniquely determined. So especially the tensor structure is uniquely determined, and what's undetermined is just the overall function. And that this tensor structure is basically given by this kind of expression. Okay? And so what's left for us is to determine this overall unfixed function. And in order to determine this unfixed function, we need to use other conditions. So what are other conditions? So one condition that's important for us is boundary Yang-Baxter equation. So the idea is that in the tree level, people have shown that the boundary, like a state corresponding to the Coulomb branch is actually integrable boundary state. But at finite coupling, of course, we don't know whether it's really integrable boundary state or not. But let's just assume that it's integrable. And if it's integrable, it needs to satisfy this kind of like what's called boundary Yang-Baxter equation, which is the boundary analog of the Yang-Baxter equation. And however, it turned out that this equation is not useful for determining overall factor, because irrespective of this K of u, you can actually show that this tensor structure guarantees that this equation is satisfied. So this is a little bit similar to the situation of the bulk S matrix. So you can actually determine the 2-2 S matrix just by imposing the centrally extended PSU2/2 square symmetry. And as a result, you discover that S matrix actually automatically satisfies the Yang-Baxter equation. Okay. So in some sense like this, you can think of this as an indication of integrability in the Coulomb branch, the fact that this automatically satisfies it. And in order to really determine this K of u, you need to use other conditions. So the condition 3, what's called Watson equation, and then condition 4, what's called crossing equation. So this Watson equation basically means that if you swap the order of particle, you need to multiply the S matrix. And that leads to a condition which looks like this. S matrix times K of minus u is equal to K of u. Whereas there is another condition which is called crossing equation, which basically means that if you have a two-particle antiparticle pair, it's equivalent to doing nothing. So there is a similar equation for the usual S matrix, and this is a boundary analog. And that leads to this kind of equation. Okay? So now our task is to basically like solve these equations. So like in the previous slide, I only like wrote like a schematic equation, but this is actual equation that we need to solve. And this is actually a complicated equation. For example, this is a dressing phase, which is a super complicated function of the rapidity. And also like this equation involves certain analytic continuation of this parameter u, because like this u is known to live on the branched surface, and then this u2 gamma requires to go to the kind of like go through the branch cut twice. Okay. So this is a complicated equation to solve, but fortunately, what we found is that actually I together with Yifan Wan already solved related equation in the context of defect one-point function. So it turned out that these equations just happen to coincide with certain limit of the equation for defect one-point function, which we studied a few years ago. So we just took the answer and then took the limit. And so this is the answer. And as a result, we get this kind of answer, so that this k of u is given by this expression. Okay? So these are what's called Joukowsky function, and then this sigma is a dressing phase. And then this sigma b is the new part, which is given by this kind of integral representation. And once you have this expression, you can also like explicitly check that these equations are satisfied by this integral representation. And furthermore, you can also do the weak coupling expansion and then see that this, like a new part, sigma b, produces this kind of interesting expression, which contains like a Euler-Mascheroni function, a constant. Okay? So combining these two, we can explain like everything inside a square root. And what's left for me to explain is the last one, which is called the kinematical factor. So let me explain what that is in the rest of my talk. So this kind of structures already appeared in other contexts in which the D-brane shows up in the context of like a one-point function, for example, like a defect one-point function or a heavy light three-point function. However, in the context of Coulomb branch, there is one new ingredient, which is precisely this kinematical factor. And so the reason why we need this new ingredient is because of the following. So in the spin chain description of the single trace operator, highest weight states of superconformal algebra correspond to spin chain states with finite rapidities. And if you want to consider non-highest weight states, then you need to consider spin chain states with infinite rapidities. And it turns out that on the Coulomb branch, only non-highest weight states have non-zero VEV. And the highest weight states have actually zero vacuum expectation value because of the symmetry reason. So we are forced to consider like some spin chain states with infinite rapidities in this context. However, like the formula that I showed, which was derived also in other contexts, were only valid and only checked for highest weight states. So we need some kind of like a kinematical factor which accounts for the difference between highest weight state and non-highest weight state, or superconformal descendants. And so this is not something people have derived before or people have studied before. So what we did was to study the tree level in detail and make a conjecture for finite coupling. Okay? So let me explain what we did at the tree level. So at tree level, what we did was the following. So as I already mentioned before, like at tree level, like it amounts to computing some kind of overlap in the SO6 spin chain if you consider operator with just scalars, and we know the exact answer. And so this SO6 spin chain is some kind of subsector of full PSU22/4 at one loop, and it can be embedded into what's called beauty grading. Okay? However, it is also known that this particular like a grading of PSU22/4 actually is not very compatible with the finite coupling spin chain description, like a finite coupling beta ansatz description. So this is related to the fact that SO6 sector is not closed subsector at finite coupling. So in order to kind of make a conjecture at finite coupling, so you need to do a fermionic duality transformation starting from this expression. And if you carefully follow the fermionic duality transformation, you discover that in the new grading, which extends, so for example, this grading, alternate grading, which extends to finite coupling, the states you started with now become superconformal descendants in this grading. And furthermore, you can very carefully follow the fermionic duality transformation studied by, for example, these people, and derive that there is an extra factor coming out if you follow the fermionic duality transformation. And these Ks are basically like a number of magnons at J's nodes. So this is a kind of exact answer for the kinematical factor at tree level. And now we make a conjecture that we replace this K, which are magnon numbers, by some related quantum numbers, because magnon number itself is not really a kind of like a good quantum number. And we replace Ks by related quantum number. Well, so of course, like strictly speaking, there is no precise logic here. We are just making conjecture. But it works. The important point is that it works. Okay, so, and then once you make this conjecture, sorry for my voice, and putting together everything, then you can actually reproduce the direct one-loop computation in field theory, for example, like so this is like a dimension 4 operator in the SO6 sector. But now, like the final answer at one loop takes a complicated form. And in the field theory, on the field theory side, computing this is actually very complicated because you need to diagonalize the two-loop Hamiltonian, which also induces a mixing with fermions and gauge fields. But we managed to do the computation, or more precisely, Kostya managed to do the computation, and then this is the answer. Okay, so, and indeed, like this is precisely reproduced from the integrability prediction, and especially like this sigma b reproduces nicely this Euler-Mascheroni constant. Okay, so I guess how much time do I have? Okay, so we have plenty of time. So let me conclude and then mention a prospect. So the main message of my talk is that Coulomb branch is integrable, and the boundary state can be explicitly constructed. And using the explicitly constructed boundary state, you can actually make a prediction about a one-point function at finite coupling. And technically, what was new as compared to like other related contexts is that you need to multiply some kinematical factor in order to account for like a difference between superconformal primary and superconformal descendants. And so there are several like future directions. Like one kind of like immediate thing one can try to explore is this like a generalization of a kinematical factor. So I didn't emphasize that very much in my talk, but like the kinematic factor, we basically only studied for certain SO6 operators. So we don't even have a conjecture for most general operators. So understanding the actual origin, or maybe coming up with some precise derivation would be ideal. And other interesting directions are like studying other observables on the Coulomb branch using integrability. For example, form factors or amplitudes of mesons. So let me mention that the form factor here is different from the form factor people already studied, because like so there are like a bunch of nice papers about the form factor of n equals 4 supermills, but these form factors are basically the form factor at the conformal point, and then they are genuinely different from the form factor in the Coulomb branch. And another interesting question to ask is to see whether there are other massive integrable theories in 4D or 3D. And one kind of like easy goals are basically probably massive fishnets, or fishnet with spontaneous symmetry breaking studied by these people. And it'll be nice to kind of like study, for example, meson spectrum and so on, or one-point function in these series. But there is also yet another interesting theory, which I wanted to highlight, which is this mass-deformed ABJM theory. So this theory is very interesting. So in n equals 4 supermills, if you do the mass deformation, you break some part of the supersymmetry. But ABJM is different. Like there is actually a mass deformation which preserves all the supersymmetry. And furthermore, like if you do the mass deformation, you get a very interesting algebra, which is actually the centrally extended PSU 2/2 symmetry, which was nicely discussed by Nicholas yesterday. And yesterday, Nicholas mentioned that there is some kind of like a three-dimensional structure, there are like central charges look like a three-dimensional momentum, but in this theory, this three-dimensional momentum are really the three-dimensional momentum of this theory. And this was also found by Nicholas and his collaborators. And so this importance of this theory was emphasized to me many times by Clay Cordova. But for a long time, I was thinking that this is just a mathematical coincidence. But last year, there was this paper by Charlotte and other people, which pointed out that actually, at tree level, if you consider a one-point function in this mass-deformed ABJM theory, it can be mapped to some kind of integral boundary state computation. So I will be still surprised if the integrability persists by this mass deformation, but at least there is some hope that this mass-deformed ABJM theory may be integrable, and it might be actually, if it's really so, it might be the first a massive integrable theory in higher dimensions. Thank you very much.
So that formula, main complication is about the operator structure. The coupling dependence apparently is trivial. It's like normalization.
Sorry, like this formula?
Yeah. So my question is actually, you didn't mention ADS5S5. So suppose how you see this result on string side, for example. So you put D3 brane probe in ADS5S5. What you do next? How you get this coupling dependence and...
Okay, so the first thing I should mention is that the coupling dependence, the explicit coupling dependence only appears here, but these are Joukowsky variables, so it secretly depends on the couplings. Okay, so it's a very complicated function of coupling.
Then my second question becomes relevant. So if you take ledge G, what happens then?
Yeah, that's an interesting question. I think we didn't study them. So there are several interesting regimes one can explore. One is to go to the short string and then compare with some flat space computation. And another is to consider some a macroscopic string and then try to construct some minimal surface ending on a D3 brane. And both are interesting questions which we didn't explore.
So you were saying how the nice thing about ABJM is that you could turn on the mass for this U1, which preserves all the supersymmetry. Is it known in n=4 that if you turn on the mass that you don't have integrability?
It's not known either. Again, I will be highly surprised if it remains to be integrable. But yeah, that's my answer. Okay.
Yeah, I mean, I guess the reason why I was asking is that 40 n=2 gauge theory I was telling you about, of course it has masses that preserve the supersymmetry. So if it's to be integrable, or it's just,
right.
n=4, the mass would be integrable.
Yeah, well, I think, right. Yeah, I think it's also interesting to think about, indeed, a mass deformation of n=4 supermills.
I think Volodya wants to ask a question.
Yes, I can repeat the question. Yes. Okay.
Question from above.
Right. Yes. So yes. Thanks for the question, because that's one thing I didn't emphasize. So this is the equation. This is the expression for asymptotic limit, and you need to correct them by the TBA. And we have some, for that like a heavy light, like a determinant single trace 3-point function, we have some like a proposal of how to use TBA to correct them. And for this one, we don't have a proposal, and that neither is true for the defect 1-point function case. And the reason is that you can try to write down some kind of Fredholm determinant, which generalizes this superdeterminant. But in the Coulomb branch case and then defect 1-point function case, that Fredholm determinant just gives infinity. And you need to do regularization. And we don't know how to do it. But for the case of heavy light 3-point function, that Fredholm determinant turns out to be finite. So in that particular case, like the proposal does make sense, but we didn't do extensive tests.
Is it the first physical absorber which depends on earlier gamma explicitly?
Well, actually, defect 1-point function, also in the defect 1-point function, this shows up.
Okay, other questions? Yes, Andrea.
The generalization of the superdeterminant, it's something that depends only on the y function of the state, but not on the boundary state. So
that's true.
Why is it finite or not finite depending on?
So it only depends on one function of the state, but like how you take Z2, so in order to define like a superdeterminant, you need to introduce a Z2 grading structure. And that Z2 grading structure is dictated by the symmetry of the problem. And for the heavy light, basically Z2 is like a Z2 which exchanges 2 wings. So that like infinity cancels between like a determinant plus and determinant minus. But that's not the case here.
Thanks.
Okay, so if there are no other questions, let's thank Shota again. And see you at the poster and at the reception later this afternoon, this evening.